Okay, how about now? Yep. Oh my God. Thank you very much. Thank you for telling me I was muted. I don't know how many people popped in here, saw my mouth moving, and decided to just move on. I really appreciate it. Anyway, I was saying good morning, Blue, and we were talking about. I was being asked about why I was taking unions yesterday, and I had an explanation. I never stopped and tried to prove it. Y'all were right. So what I've changed here, this is my search function now. And instead of keeping this ranges here, I immediately convert it to the number of combinations it has, and I just sum those up as I go. So the return type here is a long now. Instead of ranges, I then union together, which taking the union together is not valid. There's nothing wrong with my union code, by the way. It was proper union code. Hmm. It just wasn't what I should have done. It's not valid to take the unions at all. In fact, there's no way to represent your final range as one set of ranges because they are conditional upon each other. Um, yeah, so that's it now, and it's much simpler. And I was just testing out some refactors on this. Um, what am I looking for? I was working on filter by. I was looking at filter by and def matching here. This can be simplified down. I think it can just be part of filter by and filter not by. That's really the only place they're used. Um, except, yeah, you know what? I do need to have this filter. Okay, we're gonna copy paste this code and return what we had. There's some amount of redundancy here that I need to refactor out. So this should just be matching. There we go. Right, like this condition cat is just condition dot category, right? So we're doing condition dot matching condition dot category. For one, we shouldn't really need to pass that back into it. For another, maybe this should just go up in here and we match on that condition itself. Your coffee is ready, motivation is still high, and your last working day of the year. Oh yes, you can you can um stay up for a well, do you still have to take kids to school and stuff? You can at least work until or solve problems until they need you. I don't know if I'd rather have it in the mornings. I think I like that it's in the evenings because nothing else is happening. But midnight is too late. Like if I lived in California and this was 9 p.m., that might be ideal. Tomorrow is last. Okay. Um, yeah, I still want to simplify this, but I can probably simplify this. I probably don't need all these distinct calls I'm using all over the place. I was getting paranoid at some point. There, that's fine. Um, I do here. Um, wait, there was another idea. I was like, what if I wait, that doesn't even compile. No, that doesn't compile. But we could do like underscore intersect, and yeah, no, we don't want that. We flat map all the intersections, that's fine. Maybe this whole thing should be written as a for comprehension. Let's try that. The for cat intervals out of ranges. Interesting. They chose to take other intervals out of other dot get cat. And then we just take the intersections, right? Yield cat. Oh, wait a second. What is a? This is not a get. We don't want a dot get there. The other cat dot flat map. Intervals dot intersect. Yeah. Or you know what? We do this. Other intervals out of just other cat, other dot get cat, and then we yield the intersections. This is a list of intervals. Oh, I think we want. So let's just take like n from intervals, and then m. Let's just call them n1 and n2. N2 from other. Okay. And then we yield cat to n1 dot intersect n2. Not as short, but it's more readable. Oh, if we need a case here. And what else is wrong? Pound. Wait, let's look at what I deleted. Ranges.map. So for category and associated intervals, we take, and then for all the intervals of one, all the intervals of the other, intersection should give us more, it should give us optional intervals. And then at that point, we still need to flatten. Okay. I think we can do this. And then do the intersection. Oh, hold on. That's not going to be quite right because we have to keep cat. I don't know why I'm struggling with this. So we map. I don't think we can quite do it this way because for each map of this, we take this cat. Yeah, this is a flat map here. That can't be a map. Oh, yes, right. You're doing the release. Yes. I kind of wish that, like, I write some tests in here while I'm doing admin code. It'd be nice if, like, more test cases were just generated automatically. Like, that's what I want Copilot to do. Like, go in another window and start writing the tests while I'm writing the code. But then it's going to get the tests wrong, and I'm going to have to, like, debug the tests. Okay, let's refactor this a little bit differently. Put the for comprehension in here. Add one from intervals and Then from then the intersection, and then we yield cat to the intersection. Okay, so that would work. Yeah, no, it has an issue with this. We found a list of category and interval. We need a category and a list of intervals. Which list of intervals exactly is that? Um, so we are taking our intervals, we're taking the other intervals, we're turning them into a list of intervals. Oh, right. We want cat up here. We want cat, the result of this full comprehension, which I don't know if we can write that way. I have to do this, wrap that up. Yeah, that's what would work. But I don't like it. It's it's almost nice. I should just have intersect the library method. This is what I should really do. That's how I'll clean that up in the future. You work on a lot of stuff in production? Um, Not currently. Currently, I'm doing a contract to build an MVP that is not in production yet. I was working for a big health insurance company until a few months ago. And right now I'm looking around at new gigs. So we'll see what I find. But until then, this contract will keep me going. And, if I have more time, maybe I'll take, I've been thinking about doing other kind of work, but we'll see. The older I get, the pickier I get about companies. I mean, in some ways I'm less picky, but in other ways I just don't like a lot of companies. Okay. A lot of parse and code. I still don't love this, whatever's going on here. The fun starts when the launch comes, all the DevOps and scaling issues. Yeah, yeah, I'm familiar. For this contract, it's gonna be a lot smaller scale. Hopefully, not much maintenance. Um, Honestly, it could probably run fine on like a $5 server, $5 a month. Hmm. Oh, you know what? These here can be an enum. So these three things: enum action. We don't need this terminal function here. Let's take that out. Yeah, action is not enum. Extends rule, and then case, accept, reject, and send. There we go. Nice little change here, and we should import them out. Import action.star. We're still sort of using these for keys to the map. That's fine. And seal trait condition. All conditions have a category and a value. Maybe I should flatten like the operation into that. right? This is just a case class with an operation to do with the value. Hmm, I don't know. That's worth thinking about. I feel like that you could get a much nicer model out of this, but right now, like it works. Sort of just wasting time. Oh, Herrick Wassel. Yes, it is puzzle o'clock. I have my alarm ready to go off any minute. I do like my model as it is. I think some things could be changed. I don't like that it gets me to 100 lines of code. All of the all of the mechanisms are basically right here. This collapses a bunch of rules down into like ranges that go to those rules. So an action uh, and what ranges go to the action. And then the search here is very easy. Where's the other logic? This filter by stuff. Hmm. And then you have to integrate a Redis to handle the traffic. Oh no, I don't thought about that. There might be someone. Well, these would be deployed internally in the company. Like maybe fine. Um, I mean, I guess until like the customer says, "Oh, we want this facing the outside world. Oh, we want more users or whatever." I don't know. I'm hoping that's not my bridge to cross when you get there. Okay, this is fine. This is some refactoring. Eric, I really enjoyed yesterday's problem. Like I screwed up. I screwed up big time, and spent hours debugging something that I don't know. When you're doing the wrong approach, when you have a flawed assumption, you can debug it all you want, and if the code's doing what you want it to do, it doesn't matter. But aside from that experience, it was a very fun puzzle. Yeah, I'm sure I will. Next year, I'm gonna come armed with like a range tree set. We've had like 3 problems this year that deal with ranges. Not that I'd be using all the features of it. Like I got carried away, got excited. I was like, oh, I can just take union of ranges, and I didn't need to take unions here. That was silly. Let's see. Point 23, day 19, cleanup. We have 35 seconds left. Yeah, let's see what's coming. Oh, wait. We need to save this worksheet as 20. Okay, 15 seconds. We have plenty of time. I do want to make sure this worksheet is actually like rendering. I don't know, sometimes I start a new one and they don't start rendering right away. There we go. Day 20. Good data. Um, okay. Oh, is this a follow-up to the previous? Some sort of adjacency graph. Pulse propagation. Cool. Um, get down to the question. What do you get if you multiply the total number of low pulses? Okay. Low pulses times high pulses sent. Okay, so we need to know what low pulses and high pulses are. Let's see if we can try to understand this input. Machines with standard flowing. Long cables, modules attached to machine. Modules communicate using pulses. each of which is either a high or a low pulse. Sends a type of pulse to each module in its list of destination modules. Okay. High or low? A type of pulse. It can be different types, I suppose. Flip-flops. Oh, okay. Cool. Flip-flop modules are either on or off. They're initially all off. A flip-flop module. Okay. Modules send pulses higher level or low. The module sends a pulse. Okay. Modules have destination modules. Okay, if it receives a okay. Flip-flops flip when receiving a low pulse. Okay, yeah, makes sense. Just like a normal flip-flop on a low edge. If it was off, it turns on. Oh, if it was on, turns off and sends a low pulse. Okay. But only when it's low. Okay, on, off, and send low. Right? Then off, on, and send high. Conjunction modules, remember the type of the most recent pulse. Conjunction, see from each of their connected input modules. Remembering a low pulse for each input. Conjunction must first update its memory for that input. The conjunction, they have multiple inputs. Multiple inputs. They remember. Kind of pulse each input they received from each input. Okay. There's a single broadcast module. Receives a pulse it sends the same pulse to all of its. Okay. The broadcast module sends same pulse it receives. There's a button module. When you push a button, low pulse is sent to the. Okay. Pushing button module sends low pulse to broadcast. You wait until all pulses have been delivered and fully handled before pushing again. Never push the button if modules are still processing pulses. Okay. Pulses processed in order sent. A pulse is sent to module ABC. The module A processes its pulse and sends more pulses. Okay, if it sends more pulses, B and C has to be handled first. Okay. So it needs a queue of some sort. And this is a module configuration. Name, its type, and this here. Okay. We have something that's Turing complete. I'm pretty sure. Broadcaster has 3 destination modules. Yeah. Yeah, the names of the destination modules. We don't necessarily know what those are. And I suppose the conjunction modules, they don't necessarily have to have references to their senders. They just need to remember that. Remember what was last sent. So they will have a memory which defaults to low for anything. Um, okay, here's an example. The push button sends load to broadcaster. Broadcaster sends load to A, B, and C. A then sends hi to B. Um, B sends hi. So this send doesn't get handled until B receives its thing, right? And what's A sending to just B? B is sending just to C. C sends a hi to inverse. Inverse sends a low to A. A sends a low to B. Inverse sends a hi to A. Oh, okay, right. Does it really matter that a low was sent to B to start? Flip-flop module. I guess because B at that point is high. Yeah, no, B would send a high because it's received a low signal. Right, flip-flops. They start off, so they all become on. And when they're on and they receive a pulse, they send high and turn off. Okay, right, so these all like turn off. And now these turn all are off, so they turn high. Okay, yeah, let's start with that. So, field trait module. Case class flip-flop. This has on. And what else? I guess they just have off and on, and that determines what they will send. All modules can send to something else, which makes that thing receive and do its thing, and add it more. You add it onto the queue of things that will happen. And you keep going until that queue is empty. Okay. Case class conjunction. Whoops. Conjunction. It decided to import 2021 stuff. Okay. And there is a memory. And whether it received a high or low, I guess I could just use a Boolean. I don't know. I don't want to be like debugging trues and falses when we also have like true and false for off and on here. So enum, pulse, and case high and low. So from a module, we need a module name rather. So string to Boolean. So this has yeah. Well, we won't put name as part of these things. We'll just put that in the map. The val modules. Run, thank you for the follow. Welcome, welcome. Lines up to list. And we'll parse these. Copilot has no clue. Interesting, no solution submitted yet. Oh my god. It's already 10 minutes in. I spent 10 minutes reading the problem. I barely read the problem. No one better submit a solution. Okay. So we have a percent case and we have like a list of modules. I guess each module has a bunch of things it's connected to. So it has a send list, destinations, def, destinations. It's going to be like a list of string. Yeah, so that's part of these case classes. Um, Destinations, that's going to be part of the other module as well. Okay, so here is the name, and there's an arrow, and then modules, which will get split. Oh, module names, rather, right? In this case, we have a flip-flop, and on will start false. Module names that split with a comma. Put that in a different line. On equals false, and then we just have dests. We don't have this. We have name to that. Okay. Input.map, whatever. This whole thing gets turned into a map. So we're going to say map.from. Here we go. And then we have another case. There's going to be and name module names, and this is a conjunction. Map.empty with default value low. Right. This is not a string to Boolean. This is a string to a false. And then there's the broadcaster. The broadcaster module names. And let's make that here. Base class broadcaster. Broadcaster always sends whatever it receives, right? And then we can queue up sort of actions, like something sends whatever to whatever. Maybe just do like, what would that look like? Case class action, name sends pulse, destination, the string. Maybe that doesn't need to be a case class. I just felt like writing it down helps me remember things. Okay, so this is a broadcaster module. We don't need this map. Just give it dests. And there was one other type. I guess there's a button module, which means just trigger broadcaster. Yeah, you don't need to model the button module. Okay, so modules for each print line. Let's just take a look at this. Is there an issue here? Okay, currently our worksheet's not doing anything. This is worrisome. Okay, Maybe I ignore that for. Oh, here we go. Name. Oh, right. This is a dollar name here. Down below. Let's import these out. Import pulse dot star. And name. I guess this is broadcaster. Okay. And then there is like a step action of some sort. So form an action. I guess we have a state. I guess we could have like an iterator.unfold, and there's some action. And the first action is broadcaster sends low to destination for each of these destinations. Yeah, as our starting queue. Okay, so now starting queue collection not mutable. No, we don't need the mutable queue. Is queue already in scope? Queue. That's not how that works. So start maybe a queue of action. And we do need to import Scala collection mutable queue. There we go. Okay, and what will we take? We'll take the broadcaster action. Let's do the queue.from here. And we're going to do modules broadcaster. It's like as instance of it. Oh, I mean, everything has destinations. So that's cool. That destinations map. And those would be in order. Broadcaster sends a low pulse, right? The broadcast sends the same pulse it receives. And when you hit the button talks to the broadcaster. Button sends low pulse. Okay, and taking an action changes the queue up. And what will we get? What do we need to keep track of for the end? Yes, Eric Wassel might indeed be doing that. What do you get if you multiply the total number of low pulses sent by the total number of high pulses sent? Okay, so that's what my unfold would get, is the counts of low and high. Starting queue looks like this. High to GZ, high to FH. Oh, no, it could be low. Sends low pulses to broadcast. That's what happens when you hit the button. And now we're going to unfold. So unfold has the A we're returning and the state. So what we're going to return is a pair of counts for low and high. And our state is going to be a queue of actions. And we have start. Case, low, high, and actions. Or, action queue. And we'll take the first thing off of the queue. Um, we don't need all of that. So we look at what we're gonna match on the action dot sender. Yeah. So we're gonna take modules, given that name, action dot name, name being the module name. And we can match the broadcaster. Well, we've already handled the broadcaster, so let's not worry about that. Mm. The elves have pushed the button 1,000 times. Is that for part two? Oh, yes. After pushing the button 1,000 times. Okay, so this is a single push button. And then I guess there are states now. We also want to return the states of all of these. Right, a flip-flop has an on and off state. So these modules are like the initial states of these. We need like a separate. Yeah, our state needs to be module states. Then we have a queue, and we have a map from string to module. And we start with start and modules in their initial states. And we can't always start with a start, can we? Well, yeah, anytime you hit a button, it's going to be sending those. So that's always going to be our start state, our start queue, which is fine. We do also have to return that state, don't we? The final state of that. I think this could kind of be a, yeah. I should just write this as a normal recursive function on unfold. Okay, so modules, actions.name, flip-flop on. We'll take destinations.map and action. We'll do D. Let's write this way. D. And if on, then high, else low. Sure. Defaults to action.name, not to action.name, to destination. Okay, I should rename this so that helps. Rename this symbol to sender. Oh, wait. We do care about like this action, who sent that. That will matter later on. So action. We take our destinations, we map this destination. Oh, the sender is flip-flop.name, I guess. Call this dest. And the sensor is this flip-flop. It's action.sender. And I think what matters, yeah, that'll matter for conjunction. Action Q. Oh, right. You put that in. Friends, action Q is now, it should still be, well, it still should be a queue of actions. Yeah, we have type errors here somewhere. So unfold, our initial state is our actions queues and modules. Just give it a type annotation here. Queue of action, right? Actions is a list, and what we need here is new states. I think all of this can be under like a option.when action, or unless it's empty, action queue that is empty. Then we keep progressing. Yeah. Okay. Um, Now we add, the low count. So if pulse is low, I guess we can match on pulse. Pulse match case high plus 1, low. And this will be the counts. Yeah, val counts. And then we have counts, action queue dot tail, and module states, which do get edited. Module states will be updated. And now this flip-flop let me check the flip-flop rules. They flip only when receiving a low. Wait, what happens if they receive a high? Okay, so nothing happened. Wait, flip-flops can receive a low or can receive a high. Let me check the rules. Flip-flop modules are on or off. If it receives a low pulse, it flips between on and off. If it is off, it turns on and sends a high pulse. If it is on, it turns off and sends a low pulse. Okay, they only flip for, so we're going to do if action dot pulse equals low. Yeah, so now we do that dot update here. Val updated states. Okay, update, we don't update the sender. We update the destination. Wait. Match up sender. What are our first three actions? For a sec. Okay, first is action broadcaster sends low to GZ. Okay. So in all these cases, let's think about like broadcaster sending low. Action.pulse equals low. Okay, so this destination here. So this dest and flip-flop not on destinations. Oh wait, this is the destinations of the flip-flop. We want action.dest. Action.dest. Flip-flop. Flip-flops to not on and destinations gets passed forward. Okay. And we'll just say updated states here. Whoops. What did I do? There we go. Oh, low and high. High is an int, right? These should be ints. It doesn't think they are ints. It thinks this is an any. Any. Thinks module states is an any. I really don't know what's going on there. Foo, too. Like it's foo. Oh, right. Right. That's not part of the states. What what we're returning then is just a pulse sent at this point. But this returns a series of pulses. Pulse. And we return whatever that pulse was right here. Don't need to track the counts. Action q.tail, sure. Okay, I think I'm getting it. Conjunction. Yes, that's updated memory. Action.sender sent action.pulse. And we'll use the old memory inside what it's sending. Oh, we need to add actions to the queue too. So, well, new actions. Oh, hold on. We are already mapping on the destinations. Oh, in this case, we sent 3 pulses for this step. I don't know. What if we just track the pulse that was received at this moment? I think that's what we should do. That's what we're returning, not this pulse here. This destinations. This goes here. That's the pulse that's received. Action.pulse goes to action queue.tail plus whatever new actions. New actions is being defined in here. These updated states. Yeah, for each of these, I guess we're sort of like folding left on this to add. We don't need to continue updating these. This just goes outside. So that's the updated flip-flop. Right, that makes more sense. And these are the actions that are being sent. So val actions equals that. Um, oh yeah, that's simple enough. And what we can do is action queue dot tail dot enqueue do all iterable. And this is the update actions. So we don't need to define this here. Okay. Val updated actions. And here we had updated states. We record the pulse. We pass in the updated actions, updated states. Maybe I'll just start calling those new actions. Make all my future lines of code shorter. We follow that naming convention. New modules, that's what we'll call it. There we go. Okay, now we're getting it. Now I think that's correct. Okay, so these actions, the val new actions equals actions dot enqueue, action queue dot tail dot enqueue all. Pulse is our memory of the sender of action dot sender, and we send that memory. Right, let me check that rule. You remember what kind of pulse I received last from each input. It received last time, or the same pulse it receives. I think remember low for everything. When the pulse is received, first updates the memory for that input. Oh, when a pulse is received, updates the memory for that input. Then, if it remembers high pulses for all inputs, it sends a low pulse. Otherwise, it sends a high pulse. Okay, so it always send a high pulse unless. Okay. And it first updates the memory. Good to know. My notes are a little bit wrong, and it's going to influence Copilot, I think. Okay, but first we update memory. We'll call this new memory. Action sender, action pulse. And pulse if new memory all is high, then you send low. Then low, else high. And that's the pulse we sent to each of those. Great. We have to remember the pulse that the button sent, the original button. I guess it sends 3 pulses. We had those in our action queue to start, so we're good. Great. So now we have new memory. We have new actions to send. And then we have to update the state. Conjunction with a new memory. Okay. Why don't we give this a name? Val receiving module. Wait, modules, action. Oh, we should be looking in module states. Here we are mapping on the sender. I think what we meant to do is map on the receiver. Yeah. So the receiving module, does it matter who the sender of an action was? Only to conjunction. The module states action.dest. Yeah, we'll call this the receiving module. That we can match on. And in this case, it's a flip-flop. We could do like dot copy destination, except it doesn't necessarily know it's a flip. Okay. I'm glad I looked at that. I probably won't need to reference it. We do this. And I wonder if I can't just, no, I'll just do like names of modules. Oops, we don't need this. Update states conjunction. We have new memory, same old destinations. And pulse action queue, we just do new actions. And then we have updated states. And broadcaster, we're never going to have that as destination because we're not modeling the button module. I mean, we could, but we're not going to. We've already handled that. Pulse, and not pulse. There we go. Okay, so this is all the pulses from one button. And then we need the final state of that because we need to map it to another button press. Def button press. And I think what we want is a count of low, high, and then we have new states map from string to module. I wonder if I had like an entire. So this does come with modules or module states, which is this thing again. Okay. And let's make this a lazy list. We'll call this steps. And after all these steps, we want a pulse and we want the state. Type state. We map string to module. Okay, so we want the pulse and the state. That's what we are learning. So pulse and new modules. And here again, we return pulse and new modules. need a closing parameter right here. There we go. And I think we've got it. So high and low, well, pulses equals, what are we gonna do? Steps dot unzip. That's gonna be the left side. Val final state equals steps dot last dot underscore two. Pulses dot count equals high val low count. Sure, and what we're gonna turn is low high and final state. Low first. Low high and final state. Okay. Oh. Okay, I guess down here we called it new states. That's fine. Okay. Now that happens 1,000 times. So like, maybe. Let's see what happens after one time. For an example, what's this called? Button press. Let's do one button press, starting with modules as our initial state. Matter. Flip-flop faults. Line 93. Wait, 93. That's not right. Line numbers and worksheets are never right. Flip faults, false, and list of something. Said option unless. Oh, if action not pulse. Okay. We should do flip flop if action is high, right? That sends nothing. Flip flops otherwise. We should still record stuff. Basically, we do like action pulse received, and then module states action q.tail. We still take the tail and pass on module states. No module states get changed at all. Flip flop stays the same. Great. Not found Rx. Oh, okay. Module names. No, wait. Okay, let's print our list of modules. Why would there not be an Rx here? Do we like sometimes send something to an Rx? And our state starts with a get or else empty kind of thing, right? Default value. Oh, no. Okay, let's look at our input. A20.text 2023. You're close. That's good. Yeah. Almost an hour in. Okay, let's look at the Rx, for example. Interestingly, you can send to a module named Rx. Rx is never listed. Oh, that's annoying. There could be a bunch of modules that are not. No Rx module? What do I even do there? So I guess you could send to a module, but I don't know anything about that module. I guess if the module doesn't exist, let me think about that. Where does that happen here? Happening in the map. Um, I wish I could get proper line numbers here. Oh, yeah. Okay, so I'm not missing anything. I just need to think about what to do with that. Um, so we take like module states. I'm gonna rename this real quick to new states. We're just gonna rename module states to states, I guess. Um, rename this to start. I don't know. So states updated action dot destination if we have a flip flop module. Um, this missing thing is going to be one of the destinations. So when we have a look at the destinations, updated action. So destinations dest action dot center bolts and dest. We can set something as that module, and it doesn't need to have we get from maps. I'm just gonna print some outputs and then look for the line that mentions Rx. Um, print line, whatever. Not our action cues. Maybe our module states. We want to print whatever this current action is. So handling action. We'll copy that worksheet output. Scratch Rx. Okay. No, not there. Handling action. Broadcaster is sending a hi to Rx. Okay. So an action has a destination. The module states action.dest. Why are we matching on the destination? I guess we can do like a get here. Why don't we match on like sender instead of sendee? Because sender's the one that like actually kind of reacts to it. Okay, I guess Rx, we just ignore that. We look at we add to the flip flops. We're gonna do .get .match, and we can wrap these in sum. Okay, family time. Well, good luck. Have fun solving it later. Wrap these in sum. This is kind of annoying. Case none. And in a none case, we just do this record the pulse, pass on the same module states. 118, 218. And we do that 1,000 times. So after 1,000 presses, um, let's just let's just do it. So do like an iterator dot iterate. We start with modules, 0, in modules. And then we do button press. Sort of. We do a button press on those modules. Button press has to have a parameter, right? Yeah. Case, low count, high count, whatever. Plus module states. Okay. And what's for this button press to drop 100? Like that. Let's iterate. Well, presses. Or I guess it's a final count. Well, I'll make that def. Presses. So 0 would be the state after the first one, right? Presses dot next. Let's do that. 0, 0. Okay. It's before the first press. So let's make this a lazy list. I don't know why default iterator. So presses 1,000. Back again 0. Yeah, 1,000. Oh. Oh, it's gonna be too slow. No, okay, it worked. It worked. Great. So let's take out some print lines. Handling action. Yeah, great. Let's actually get these values and compute something with it. Low, high, whatever final state. Presses 1,000. Now ends 1 equals low times high. Yeah. I'm worried I might need to convert that to long. Let's see. So is part 2 going to be like, do this a million times and find the repeats or something? We didn't have like a stack overflow last time, right? No. I feel like I was getting better performance in the iterator because that finished, didn't it? Excuse me. Iterator dot iterate, and then presses dot drop 1,000 dot next. And we're just going to do it too long, just in case. It says it's still valuing the one from earlier. I'm just going to restart this real quick. And while that's happening, let's think about performance optimizations. So each step through here, we look at the whole map of whatever probably a button press can be memoized, right? Because we might have maps, say, at a similar state. There's certainly like a cycle in there somewhere, right? How big is this thing? Date 20 dot text. Maybe I should be trying this with an example first. Well, while this is running, has it run yet? I don't think it's even trying to run. Still, let's make an example file. Um, First example, wait, what examples do they give values for? In the first example, the same thing happens every time the button is pushed. 8 low pulses and 4 high pulses are sent. Okay, in the first example, 8 low and 4 high. Uh, in the second example, so this is the second example. Let's copy down the first example, because that will be, here's the second example, here's the first. Okay, now let's copy that example 2 as well. Go back to our worksheet. Still being evaluated. We had, wait, recursive value needs type. That's not recursive. It's patently not recursive. Like, what's all this? We have other issues here. These issues have nothing to do with my code. These are worksheets just bugging out. Oh, that's annoying. Okay, let's see if it tries to interpret this. Like, maybe I should comment this out first. Next time I close this, I'll comment out this line first. Make sure it can do other things, like work on the examples. Okay. I am willing to wait for this. And while we wait for that, let's think about optimization. My best idea is to memorize, look for potential cycles. I guess memoizing is the first step to looking for cycles. If memoizing works, then there's a cycle in there somewhere. And then we could probably speed up some of these, like, I don't know, maybe like certain subgraphs. Okay. Hey, this ran. Sort of. It ran for a lot of this, but how many types for that? Just compile it. I wish I could get this out of the way. I can't see this. Okay. 1.25 seconds. I don't believe that. Okay, evaluated in 51 seconds. And there's all this other stuff happening. Okay. Make sure this is working again, and we're going to try this with an example. So we'll try a single button press, see what happens. We should at least get the right answer there. Oh, oh. Still importing build. Comment that out for now. All we're doing is button presses on the example, right? So when we restart this, it should be easy. I know. Let's let that run. I just want to check out how leaderboards are doing right now. Fewer than 1,000 people have finished altogether. We're at 1,400. Okay, so we're getting to about the point when I should be able to finish. And look at leaderboards. So on my leaderboard, Nikki and Alexander have finished. Makes sense. And on the Scala Center leaderboard, 3 people have finished the first part. Merlin Org and Java Doc are always so fast on this one. Um, this is returning a 7 and a 4, and then those states. 7-4 is not what I'm expecting, is it? 7 high pulse, 7 low pulses. It should be 8 and 4. So we're missing an 8 somewhere. Actions we're handling, because each of these actions represents a pulse, right? I guess a button, does a button count as a pulse? Button sends a low. Yeah, button sends a low to the broadcaster. Okay, you know what, just so we're modeling this properly, because we can't like button every time. Gonna start with modules. Our start. Oh, hold up. This is gonna be the wrong answer when we repeat, because this start. No, okay, the start is always gonna be something. Let's define this up in here. So the broadcaster sends whatever it receives. So this is just going to be a view of action button sends a low to the broadcaster. Okay, now we're handling that action as well. And if it is a broadcaster, then what do we do? New actions. Action queue.tail and queue all of these. Destinations map, action, sender, action not pulse. Wait. No. Action not best. Because a dest is not a new sender. Man, autocomplete is dangerous. And then no, no module state should change. So this is good, right? All that's really different is that. Okay, so I'm gonna do this. Val, L, H, and state. What's that? L times H. L is 8, H is 4. Okay, that's good. Let's look at this for example 2. Oh boy. Immediate. Oh, example 2 is not actually an example. Yeah, let's copy the proper thing here. Here's a more interesting example. Go. Okay, let's run that. So after one run, it's 4 and 2. Pushing the button once, the following pulses are sent. Low, 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 high, 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 low, 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 high. Well, that's not the answer I got. I got low 4 and high 2. So we do have a bug here somewhere. Button, low, broadcaster. Handling button low broadcaster. Handling broadcaster low A. Broadcaster low. Oh, wait, this is for the first one. Okay, for the second one. Button low broadcaster, broadcaster low A. Broadcaster. No. Sends a low to inv. But broadcaster is only connected to A. Why is it showing broadcaster sending these to everyone? Because destinations, this is just. So I mean, this is sort of correct. Button low broadcaster, broadcaster low A, and then there's a low to inv. That should be inv. There's low to con, and then there's a high to B, and a high to output. So that's fine. Low, 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 and 2 highs. 4 lows, 2 highs. So I mean, this works. This works. It's just not performant enough. And yeah, first thing I'm gonna do is memorize it. I should stop talking about memorizing and just do it. Actually, first thing I should do is fix this. New actions. Not dest. I guess this action was from. Wait, but broadcaster. You'd only enqueue that one thing, right? And then once A receives something, what type of thing is A? A is a flip-flop. Okay, and it's going to receive a low, which is good. Dot dest. Yeah, they should all be action.dest, not action.sender. The previous action. Its destination is this next action sender. Man, that's confusing. Wait, maybe I was fighting with autocomplete. Was like autocomplete correct there? Okay. A low invid, A low con, inv high B, con high output. Okay, so we have the correct count, right? But is that the right thing? Button low broadcaster, broadcaster low A. A should be sending a high. A sends a low to inv, and then a low to con. So broadcaster sends a low to A, and A, I guess, turns on. And then depending on that new state, like that, flip-flops, they're initially off, ignores the high pulse, receives a low pulse, it flips. If it's on, it turns off and sends a low pulse. So what it sends is going to be like opposite. If it is off, it turns on and sends a high pulse, right? If it's on, it should send a low pulse. Wait. Yeah, it flips. If it was on, it turns off and sends a low pulse. You know what? I remember correcting Copilot there. Copilot was right. Um, yeah, okay. Now let's look at this. And we have button. Where is this? No, it's lower here. Here's a more interesting example, and here's the result of that. So button low broadcaster, broadcaster low A high inv, A high con, inv low B, con low output. Oh, wait a second. A high inv, A high con, inv low B. Con should be high to output. B high con, con low output. Okay, con, which is a conjunction, be sending low to output. Oh, con doesn't necessarily know about all its inputs yet, does it? Well, no, it remembers low for everything. Con has to know all of its inputs to do anything, not just the inputs it's received, because otherwise it has no way of knowing if all of them, right? The conjunction module first updates its memory. If it remembers high pulses for all inputs, it sends a low. In this case, conjunction sends a high because it doesn't remember high for everything. Because B hasn't sent anything to con yet. And now con sends low. Okay, and it's not going to check B. Okay. As to have, you can't do a map with default value. Um, okay, well, I'm just going to do something quick and dirty here. Our input is small enough, it shouldn't matter. So conjunction now has, it still has memory, but we have to get all the inputs. Well, inputs equals, what are we gonna do? We're gonna do like input dot collect case. There's a simple um, name. Wait, broadcaster could also send to this thing, right? Okay, this is the dest. If dest equals the name, send. If dest equals name, then we collect just those destination, those senders. Um, yeah, we'll call them inputs. There's a percent, there's the and there's just whatever. What if there's a button? What if the button's connected to it? No, the button only ever goes to the broadcaster. Okay. And we can do inputs.map um, I to whatever. Was it to low? Everything starts low. To map. Okay, now when this works, con sends high and then con sends low to output. So con sends high to output and then con sends low to output. Cool, that works. And when we run that 1,000 times, check that we still get the right answer there. 1168 7500. Okay, yeah. Now we just optimize. I wonder if this is partially because I'm using like mutable queues and such. Mutable queues is probably fine. We are returning like all the module states because like that needs to be passed on. Memorize, we memorize. Do we memorize per button press or per, I don't know, look at the module state. Say a button press applied to module state, it'd have to be narrower. And what would the result of that be? It'd be like, okay, these actions get queued up and this portion of the module gets updated. Module states aren't always updated. We just start with flip-flops. Well, yeah, flip-flops in conjunction, sure. Because flip-flops will flip. And conjunctions have Memory. Let's just do it for full button press. Okay, in that case, we have a calculation. I guess this thing is the calculation. I think we just want to memorize like the final state of that. Or this whole answer, I guess, is what gets memorized. Yeah. Um, val, memo, post collection enable map. And just a module is just a state. State to int, and another state. Always gonna have that start state. This lazy val calc equals all of this. I'm just gonna indent that. And then we're gonna do a memo get or else update with the calc. Memo type get or else update. Modules and calc. What is the second argument? That is delayed. Cool. Okay, so this still works. Let's see if that improves. Performance in the full answer. 980. Okay, that was instant. 980-457-412. 980-457-412. How long was I saying I should just memo? It took me that long to actually do it. But do it, I did. Named RX. The machine turns on when a single load pulse is sent to RX. Reset all modules to default states. Waiting for all pulses to be fully handled after each button press was a fewest number of button presses required to deliver a single load pulse to the module RX. Okay. Let's see. Just a single load pulse to the module RX. Okay, so you have to count pulses to everything. So instead of just returning pulses, we're going to return a list. I guess like a map of a list of pulses sent and received. We can do this very quickly. In fact, 1001, I'm not being in the top 1000, but I'm going to be 1000 something. Single pulse. Set pulse and state. There's going to be a map. A map from string to a list of pulses. I'm going to say this right now. Add day 20 and 23 day 20 as solved on stream part 1. And we're not going to make this work for part 1 anymore. We're just going to completely kill it. So this is a map from string to a list of pulses. Do action.pulse Um, no, this isn't going to return a map. This is just going to return all those individual pulses. So, return a. Wait, we can just return all the actions. Yeah, we can just return all the actions. The action that was handled. Okay. Not returning action on pulse, just returning the full action. This is now actions. Val pulses. No val pulses. Actions.map pulse. Okay, nothing changes right now. And what we also want to return the counts. I think I'm just going to do the count. Actions.count case action from sender doesn't matter. Low pulse. Or, we're going to filter. We're going to filter for pulses when the sender going to collect. Dest, if dest equals Rx, then we get that pulse. And val Rx pulses. And let's just return Rx pulses here. Hopefully my memo still works, right? Just a pulse. And here, return a list of pulse. Wait, we have other things going on here. We're just ignoring the pulses. In fact, we comment all this out because we don't need that to work. We don't need this to work either. We're just going to do presses. Oh, we still need to iterate. Okay, we still need these presses. So we do need to get that to work. Button press now returns 4 things. I guess we returned a list of pulses too. Rx pulses. Oh, and this is just going to be list of empty pulse. Yeah, right here. So Rx pulses. Well, new Rx pulses. I mean, I think we can ignore this. Okay. So this still works, right? Found in int state bolts. Required in int state list of bolts. Oh, here. Let's look at calc. List of bolts. Let's Rx bolts. This is a. Okay, let's two list this. Okay, we're still getting the answer. Now we take presses. Make this a def. Presses dot. I wonder what the first Rx bolts is. Let's just make sure that's something. Okay. Presses dot index where Rx bolts is equals a list of just low. And it's gonna be +1 because 0. Wait, 0 is just gonna return us the initial state, right? Presses dot next. I hate these off by ones, but I have to think about them. This thing actually seems to take a while to run. Okay, 0, 0. And the initial hash map. Okay, so we're gonna take that and do +1. L adds 2 equals 1 plus presses dot index where Rx bolts is just a list of single low bolts. And that index is apparently going to be a lot larger than 1000. No, it's ends 1. Let's halt running and start running again. It seems to be in a death loop. Just restart this. Okay, so wait for this to run. I'm just gonna check the leaderboards in the meantime. Okay, I'd be the second to finish on the Scala leaderboard if I did this right now. Just wait for my worksheets to come up. Indexing complete. Calculating. Taking a while just for part 1. I remember part 1 being a lot faster than that. Okay, it took like 20 seconds to run part 1. Well, I'm gonna let this run. And I have to do something smarter than memoizing. Wait, it ran 12 seconds. It's done? Out of memory error. Java heap space. Okay, we're doing an iterator.iterate. And on each thing through, we're getting modules, list of pulses, yada yada. Garbage collector should be able to handle this, right? We are adding stuff to the memo on each run. We can refrain from adding the list of pulses. Oh, how would that work out exactly? We'd have to give a false answer for our pulses, which is not even going to be a single low pulse is sent to Rx. Hmm. I guess we could have a none. This none only happens for Rx, right? We could go back to returning just the pulses. Um, I just like increase the memory I have. All this in a REPL. All the modules anymore. We're in SBT with extra memory. I'm tempted. So SBT, what's my default? No, I forget to expand the alias. Whatever, we'll do alias SBT. 24.8. So alias, so we're gonna do like SBT with mem. Give it 20 gigs. An order of magnitude more. Console. Copy paste all this stuff right in. No, you should not be trying to run LMs2 not until I think about more performance optimizations. All right. Oh, I'm doing all the print lines for the actions. That's gonna slow this down. Oh no. Ah. Okay. 3. Used 14. I don't believe that. By what? I don't know. Maybe we'll do a quick kill all Java. Kill all Java. And then check free. Used for free 16 gigs. WSL will give me more memory if I need it, right? So let's do this. Speed TMM 20 gigs. And we're gonna let that run in the background while we're trying to solve stuff. Oh wait, the print line. Handling action. There we go. Let's get rid of that. And here goes nothing. Oh wait, console. We can open up a console first. Here goes nothing. Wait, is this running? Should be going. I don't know what the deal is. Well, that's trying to run. Let's look at other ways to optimize this. We need to optimize memory, really. Well, our memo gets big. Oh, you know what? This is a cycling problem. The first time a state reappears, right? We don't need to use a memo if we already sort of know what things are. So we're going to remove the memo altogether. Or we can use the memo. Find the first repeat. So which one had that? Git ls files, got 2023. Xargs grep repeat day 14. Let's just copy paste that code. Pulling it up on the right here, day 14, 2023. Okay, cycles here is steps. Or presses rather. And we could do hashes to find a repeat. Yeah, let's just follow the same pattern. We don't have to think. L hashes equals presses.map 3.hashcode. Right, that's the modules. Now, scene hashes. Oh, exactly, hashes scan left. I'll repeat. Um, and then I guess first hashes dot index where equals the hash repeat. That's our ends too. Where's the ends to? I need to do one plus one. No, I think it's actually just the index. I don't think I need to do it. Ends to equals first. That's it. Let's try for the example. So we're gonna run on the example here. Dash X. Find my formula on the example. Value hashes does not take params. I mean, what is. Oh, this is a lazy list. I don't know that I wanted it to be a lazy list. But it will be now. And let's look to the examples. Nope, they don't. There's no Rx in the examples. So, whoops. This is just going to be on the actual input. Let's run that. See if that looks better than running through everything with a memo. Running through everything with a memo. It could just be that it's like well over 1,000 that this happens, right? Which is why this is slow. And there's not going to be. Oh, we're going to get the index of the first like repeat of a map, which does help in the first 1,000. Oh, and then somewhere in the first whatever does repeat. So it's going to be somewhere within 10,000, right? It'll be somewhere within 10,000 that this happens, or 1,000 that this happens. Let's back off a bit on this. Okay, let's see that we can still get hands one. Cancel this evaluation. We should still get the answer. Versus what happened here? Yeah, this is going to be back to an iterator. Right? And it repeats. We can count the memo hits. If memo dot contains modules print line memo hit. And where does that happen here? Where does that get printed? Is there never a memo hit? Does the memo not matter? Comment this out. Just return calc. Manage 0, whatever. Oh, wait, I never needed the memo for part 1. In that case, not going to be within the first 1,000. Memo was useless. I think changing from an iterator, from a lazy list to an iterator is all I needed. Wait, I spent so long worrying about performance on that. I guess it was not necessary. Is it the fact that I had a lazy list originally? This runs in like 2 seconds. Okay. It'll just be presses 1,000, right? And my computer is like starting to crawl. This stuff never really ran, did it? Oh, wait, it's still running in the background. Ah, yes. A lot of time spent in GC. A big reason for GC would be that memo. We remove that memo altogether. See what we get. So ends 2. We can delete this. I think I want to stop this from running. It's taking all my resources. 20 gigs, 10% of my CPU is in heap, or like 100% of my CPU is in garbage collection. Yeah, okay. How are we doing now? Let's just do a kill all Java, -9 Java. There we go. I guess we can restart VS Code. We're gonna do this without the memo. That's just taking a lot of space for nothing because apparently it's not what we need for performance. Memo. Actually, we're not using the memo, so that's cool. That's a lazy list, I guess. Ends 2 is just this index where, and in fact, I don't think it's even a +1. Let's just get the index where. Goes through 1,000 in like 2 or 3 seconds. I wish I had an idea how big this is, because like I can calculate this. So right now it's gone through like nearly 10,000. It's gonna be 100,000, then uh, you have to wait another 4.5 minutes. It might be necessary to do like some state analysis. And KL. So when does it send a low pulse? It sends a low pulse when all of its inputs are high. Right? So when do all of its inputs go high? All its inputs are other conjunctions. So when all the inputs to that are high, to those are high. They give up. The lazy list isn't a death. Garbage collect the beginnings, right? We're gonna cancel this. We convert that to an iterator. Should be able to garbage collect that pretty aggressively. I copy paste this into the REPL again. Yeah, let's make sure ans1 still runs, I guess. Okay. Give it 20 gigs. So we're gonna copy paste that in. Currently evaluating. I don't know what it's doing. So other ways to like optimize this besides memoizing, it could be like some sort of analysis, right? We could look at what happens on. We could analyze on each step what actions get sent, and look at each of those, and that can help give us some sort of idea. Um, that seems to be okay. So that's running now. Why is this not running anymore? This is presses dot drop 1000 dot next. Yeah, these are not applicable. These errors right now. To restart the server. And while this is running in the background, this right here, I could do some analysis. How's my solving going? Well, I got part one. I thought I needed to memorize, so I did memorize. It turned out that was not necessary. I don't know if that's too much of a spoiler. But now part two apparently needs to run many more times. Um, and it's taking too much memory. So I'm gonna do some analysis and see if like maybe the solution of part two isn't to run it, but is to like be a little bit smarter. Like look at RX, look at what goes into it. How long is it? Yeah, my code takes about 6 seconds to run part one. It keeps repeatedly running part one for some reason. For this, we'll want a lazy list. We'll look at various values. This is an attempt at cycle detection, which I don't think is the answer here. I was hoping there's like a cycle at some point before this happens, but we're looking for the first time this happens, so that doesn't matter. Yeah. I mean, when I tried it without memo, it wasn't performing well. I thought it wasn't running. And then I added memo and it worked. And I removed memo and it still worked. So I don't know what happened there. Um, okay. Let me delete this stuff. That stuff can live down there. Okay. Now, lazy list, we're going to do some examination. Uh, and I think I need the actions to be returned. Right now, I'm just returning the pulses. Yeah, I'll just return all the actions. Um, list of actions performed. And what's wrong with cool? Oh, we need actions up to list. Okay. Presses 0 should return nothing, right? Presses 1. I think my worksheet is struggling because of the thing I have running in the background, which is not going to complete. I'm kind of hopeful. Like, I don't know, if I'm on for another hour, maybe 30 minutes is enough. Who knows? If I can run through 1,000 in like 5 seconds, and we need to do 100,000, that's like an hour. I can solve it then. I just wish I knew how large a number we needed to get for the second part, right? Um, wait, gears are spinning here. Sometimes it tells you if an answer's too high or too low. 100,000. Let's just say that. 100,000 is too low. Oh, okay. Um, yeah, this is gonna take at least an hour. So we need to do something way smarter. Um, I wasn't exactly brute forcing. I was like memoizing, thinking I'd see like states repeat. Uh, but yes, I've so my thoughts here are to do analysis on Rx. Look at what goes into it. Rx is a conjunction point, so everything that goes into it has to be high. Everything that goes into it is also conjunction points. So all of the things that go into there have to be high. So I'm gonna try and figure out like what needs to happen for that to happen. Um, and what happens on each press, which I currently can't do. I can't even do analysis right now because this is taking all my compute. So I'm gonna kill this. Kill all SBT. Even my terminal is laggy. Kill all Java. 21 gigs. Our CPU. No, too much stuff is running. A lot of stuff inside VS Code. Okay, I think we kill VS Code. Then we're just gonna kill all 9 Java. No. Okay, no Java processes. And what modules go into? Let's do this. Modules dot filter. Destinations. Every module has destinations, right? But oh, yeah, we want once I go to RX. I didn't know what modules value stuff filter destination contains. Oh, you know what? Hold on. We want to collect here. Collect case name module. If module destination contains RX, then we return the name. Or you know what? I can just open it. Day 20 dot text. So which one's going to RX? KL. Wait, just KL? Oh yeah, KL goes into RX. What goes into KL? Oh, oh, oh. I need those module names and I need the flat map. Let's do something like, wait, why is this not running? My worksheet's just not running right now. My computer spans are spinning like crazy. So what's going on? Like I'm not actually trying to compute anything. Handle that. Um, man, I love worksheets, but sometimes they just die on me. I don't know what to do about it. Okay, so which ones go into KL? ZC, MK, FP, XT. And those are all conjunctions. So for KL to send low, all of those have to be high. MK, yeah. MK. This is and FP. And KL. And we'll take a closer look at what goes into that. L next T. Okay, XT is not a conjunction. All of those are conjunctions. So what needs to go into there? And part of what I want to be able to analyze here once this is ready is look at the state. Look at how the state of these modules changes on every step. Okay, so let's start with like MK. Okay. Like maybe I could like prune this whole thing down and like get rid of things I don't actually need, right? MK comes only from LL. That's the only input. So LL needs to be on. And let's take a look at LL. What goes to LL? A lot of things. And now we're starting to get flip-flops. In fact, they're all flip-flops. Everything that goes into LL is a flip-flop. Um, Okay, let's look at these. Starting from the top, I guess. UD, UD, ED, MR, UD, PD, MR, MX, FH, EH, MX, FH, ZH, BL, SQ, BL, SQ, and TX. Let's see what goes into FP. FP is one of the ones that go into KL, so it needs to be high. No, it needs to be low. Wait a second. So we need low to go to Rx. And everything going into Rx is a conjunction. Conjunction. Initially remember all low pulses when the pulse is received. If it remembers high for everything. So all of these need to be high. It's high. And for that to be high, that's kind of its default. Wait. If it's all high, it sends a low. Oh, okay, so, right, conjunction, it's just and. Yeah, exactly. So all of them need to be high, which means all their inputs, all of these flip-flops need to be high as well. Oh. And we could see how those flip-flops are changing. Maybe each of those has a cycle. My worksheet is still not running. I don't know, it's just like very dead. Am I getting any output? It says it's analyzing the worksheet. It says it's running the worksheet. This is probably why I thought part 1 was not running without the memoization, because my worksheet just died. Oh, I love worksheets, but I hate when this happens. But we can keep analyzing. So FP, there's only RC. So there's an end RC. It feels like maybe it's a reverse engineering kind of thing. And then everything that goes into RC, I'll bet, is a flip-flop. Flip-flop, 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 flip-flop. Okay. And some of these same flip-flops also go into LL. I don't think they can go into LL for this to work. And then what do we have here? A bunch of flip-flops. Okay, I think understanding the structure is important. Let's look at what goes into XT. It's just gonna be one thing. Yeah, just GV. Only one thing goes into XT. So XT needs to be high. Another bunch of flip-flops. Let's look at KL. Oh wait, we haven't actually looked at that. GV. Flip-flop, 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 flip-flop. Well, let's say 4 flip-flops this time. 4 flip-flops. Probably went into RC. 5 flip-flops. That matters. I think that matters. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this takes 9 flip-flops. Again, all those flip-flops need to have high, so all of them need to have an odd number of flips in a single button press cycle. And what has memory from? I mean, everything has memory. Flip-flops and conjunctions both had memory from the previous cycle. Okay, what goes into KL? I mean, we could simplify this graph a little bit, right? Like, if KL is only gone in by XT, then KL is essentially going to be the same thing as XT, whatever it is. So we can like prune this tree down a little bit. Redundancies. So XT goes in there. Oh, XT is the same one that goes into, wait a second. Okay, so what goes into RX? KL, yeah. Oh, wait, KL? This is a loop. No, that can't be. It goes into KL. KL, we have MKFP XT and ZC. Okay, this is actually ZC here. ZC. Okay, that makes sense. Now looking at ZC. And QF goes into it. And what goes into QF? There are 8 flip-flops going to QF. Right, those are all flip-flops. Okay, and I want to figure out what each of those flip-flops are, so I'm gonna write code like modules, not filter, destinations contains MK, no, not MKLL. Yeah, LLRC. Wait, XT goes into XT? I don't believe that. That's wrong. XT. GV goes into XT. And then GV has 4 flip-flops, right? Oh no. GV has 9 flip-flops. Okay, LLRC, GV, and QF. And I want to see if there are any overlaps between any of those keys. Not found type actions. Oh, list of action. Found RX pulses. Oh, okay. Our worksheets are working again. RX pulses are now actions. Okay, our worksheets are working again. Great. Let's name these val into whatever. So we have into LL. RC, GV, QF, and then we want the intersection of all those into LL dot intersect. Or yeah, let's just do a list of all of those. It should autocomplete. There we go. Um, reduce with intersect. Um, oh, okay. Let's map those to sets first. Dot map. Use sets. Dot reduce with intersect. Um, empty set. So they are all unique. Oh, some of those I count more than whatever I'd counted here. Let's take a look at that. Oh, they all have exactly 1, 3, 4, 5, 6, 7, 8, 9. 9, 9, 9, and 8. Interesting. That is not what I counted. Like LL, LL. Oh, yep, there are 10 matches there. Was I looking at like the match number? Or is my text a20.text? So LL. Yeah, there are 9 of those. And it's just RC, there are 9 of those. And they are all flip-flops. GV has 9, and QF has 8. Interesting discrepancy, right? QF has 8. Okay. Um, and none of those intersect. What I'm gonna do is check if any of them, any pair of them. So we're gonna do like combinations 2 dot exists case intersection is not empty. Let that run. I think our worksheet decides to concat again. Oh, it doesn't allow worksheet. Okay. 9 flip-flops. This is 9, 9, and 8. Okay. So each of those has a separate line. And 9 times 3 plus 8 is 8. 35 lines are devoted to that. And then there's 4 lines for each of these conjunctions that all the flip-flops go to. And there's another 4 lines for the conjunctions that those go to, and then there's another one for the RX. So let's sum those up. How do I do this? Plus 41. And let's look at modules. That size. 58. So what are those other lines? Broadcaster goes to GZ, which is interesting. That's one of our. Wait. No, 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 that's not one of our things. Hmm. each of these on the line where they like show up right away. How do you do this? Okay. And how far are each of those from the broadcaster? Are any of those GZ? Yeah, so the broadcaster touches that. Uh, GZ, FH. I think for each of those, we want to know like which ones go into it. Just look at an example of something. Um, let's look at VL. Is reverse engineering the problem? Wrong way to do this. My first idea wasn't to reverse engineer the problem, but to get an idea of what's going on. Like reverse engineering would take too long. Okay, FH goes to LL and VL. Wait, LL. No, VL goes to LL and VG. FH goes to VL. Does FH show up anywhere here? Yeah. FH goes to VL. These flip-flops go to each other. Okay, for each of these, we're going to take this, for example. Dot flat map, dot filter, destinations, copilot, you should know. Okay. And then I guess dot keys. I should filter we call dot keys. No, not contains LL. So we have a node, a module, and then we do modules.filter contains this module. Wait. No. 10. There we go. Those are all the things that go into the keys of that. Each of these are sets. That's returned as an iterable. I guess this is clearly, yeah, these are clearly sets. We don't do a flat map. Let's do a map. Let's look for overlaps. So that map, these for each of those, the to list, and for each print line. We copy paste this analysis for each of the other two. Yeah, so we have a mess here, a bunch of flip-flops. Mhm. If we mapped each of those to modules, their starting positions, the kind of modules they are, flip flop broadcaster, right? And each of these is actually only a single thing goes into it, except for one piece, which has a broadcaster going into it and a conjunction. Mhm. Yeah, let's try this. Into RC, into GV, into QF. And I think after this, I'll have enough data. I don't think it should be possible to just reverse engineer the whole thing. Um, Okay, each of these has one element that the broadcaster goes into. And I think, yeah, let's print those again, but we're going to keep the module name as well, right? Like that. And two, whatever. Okay, now GZ is here. FH is not in this list. JT and VJ. Wait, FH, VJ. Oh yeah, GZ, JT. So the broadcaster affects one in each of, each of those, but also a conjunction. A conjunction goes into each of those. Each of those they have one broadcaster and one. So each set of these flip flops that goes into our main conjunctions has one conjunction and one broadcaster going into it. Do I recognize those as SQGX? Those are not these. These are all the things going into that conjunction. So that would make it send a high that gets ignored. So this conjunction is pretty much always going to send a low. I mean, hopefully, I don't know. The broadcast will also send a low. So on every turn, each of these each of these four get hit. Um, and I want to know where each of those four specifically go. So let's look at those. So modules. You look at the broadcaster, destinations. And for each of those destinations, we'll do this thing. So each of these things goes into a conjunction, uh, has a conjunction that goes into it. Wait, is that right? Yeah, each of these things has a broadcaster and a conjunction go into it. And these are the things that it goes to. I think that's all I'd wanted to print. Let's go back to the worksheet. Um, Modules that filter, map modules, and then do destinations. Because we end up printing a module, right? Oh, no. This is a conjunction. Yeah. That's the things that go into the conjunction. I guess it goes into these flip-flops that also have conjunctions going into them. Uh, I'm just gonna grab a snack real quick. Be right back. So I think these conjunctions are pretty much always triggered. What do each of these go to? Like these each go into a conjunction that will then send a low. I wonder where these other LL is one of our conjunctions that goes to another conjunction, right? One of our final conjunctions. Into our KL, right? Um, so XTLL. So MK is basically a synonym for LL, sort of. Basically, LL will have the same result as MK. But LL has a bunch of things that go into it. It doesn't go into anything else. Okay, yeah, LL. Excuse me. Okay, LL goes into a bunch of other things. RC also goes into a bunch of other things. I assume GV does too. But these other things, where do they appear? I assume they're flip-flops. Look at like a easy. Is this in here somewhere? All right, these are these things. So these are the four conjunctions that lead to the They're the four like penultimate conjunctions that lead to the four conjunctions that need to lead into Rx. And each of these conjunctions have a bunch of things going into them from all over the place. J, does PJ appear elsewhere here? Nope. See? No. Okay. Oh wait, these are destinations for these conjunctions, right? Not the things going into them. Well, hold on. No, that is it. Oh no. The inputs are here. And each of these conjunctions has a single input. Um, yeah, the broadcaster goes into four conjunctions, like FH. No, the broadcaster goes into four flip flops. JT and VJ. Oh yes, yeah, they're exactly these four, right? But each of these four initial flip flops also go into a conjunction, my conjunction data type. So memory of what goes into it, right? And then a list of destinations. Um, hmm. And the SQ, one of these other flip flops go into it. I'll have a single flip flop going into them, and they come from the same set. Yeah, comes from the same set. This comes from the same set. Into QF. So these are the things that are going into QF. They should all have QF in there. No, that's destinations. This one doesn't seem to have that. These are the modules themselves. Oh, right, these are the destinations of. Oh, hold on. I forget what it was I was drawing out here. So, modules, filter. So these are modules that are going into the modules going into these QF. So say QF, JT through CL, and we did the same kind of thing. So QF, JT through CL, yeah. And then we're looking at the things that go into these. Most of these, it's a single flip-flop that goes into these and into other things, apparently. When they go into other things, that other thing is the same QF. Hmm. I think I want to get like the name of each of these modules. So JT goes into QF, and then something else goes, right? JT goes into QF, TS goes into QF, but also something that goes into it also goes into QF. And then this is a flip-flop that only goes into RD. I want to know the names of that. So map modules, we'll call this N, and we're going to do N modules N. Oh, right. Mm-hmm. I have a strong feeling that I'm doing too much digging into this, but for what it's worth, I am enjoying it. Okay. Um, yeah, so most of these only have a single one going to them. So VK flip flop goes into. I should just kept the name in the case class. And VK apparently only appears within this set here, right? MZ is another one of these. TZ is another one. No? I wonder what TZ is. It does show up in the destinations for the conjunction. Junction that goes into GZ. Wait, TZ. That doesn't appear anywhere else, at least. Um, GV. A bunch of these go go into GV. Um, and I think all these targets are flip flops. Flip flops within this very set. KX. I don't know where that is, but I think that should be disjoint. Yeah, I should draw this out. Let's just straight up draw this out. Hmm. Yeah, I do feel like I still need to understand this more. And I want to draw. Let me try that. Hmm. Yeah, so it looks like I'm going down the reverse engineering track before I commit to it. Let me think. Um, not just performance optimization. He said 15 digits. Thousand, million, billion, trillion. That's gonna be a multiplication of a bunch of numbers. Of four numbers, I think. Of four numbers in the thousands, which are themselves probably gonna be, yeah. You have to fully analyze this. Let's do it. Let's do it. Mm, I want to get a call. Whatever. Why is your tongue so long? What do you mean my tongue? Oh, you mean this pen? You can't even see my tongue. All right. Maybe I'll use different colors for different types of conjunctions. Um, let's start out. Uh, sure. Let's see how big these lines are. Go on, zoom a little bit. Okay, so in the middle of this all, we have an Rx, right? Rx pulses. And then we have these four going into it. Where'd my pen go? I can't draw without a cursor. I don't know. Try this again. Okay. Let's go into here. And let's start with white. So there is a big Rx in the middle. And how is day 20? Well, part one is fine. Part two, I feel like I'm analyzing part two because I need more performance, and I don't think it's a matter of. I think it takes some sort of analysis of all these pathways, and I don't really understand what's going on there yet. Wait, there's an analysis I forgot to do. And that is as this. Um, I should look at how inputs change over time. I was just about to like straight up reverse engineer the problem. So presses, let's look at this. So presses 0. I think we want the actions dot underscore 4. And yeah, that starts off empty. Right. Let's do 1, 2, 3. Let Copilot complete the rest. Hmm. Hmm. So there's bunch of highs to Rx at the very end. Wait, from KL? Because I guess KL gets hit a bunch of times. Mm, I don't know about those yet. We could look at how the state changes for any of these. So let's look at these three. Or let's autocomplete more. What I should do, well, I like those appearing in their own lines. I should do like for each of those. No. Let's do like a 1 to 10 where each prints all the maps to it. Or let's start with this. I want people to look at each one at a time, so we'll put them on separate lines. And oops. 3. Oh, yeah, for each of those, I want to do it for each print line. It looks like they all appear in the same order. So the flip-flops, they all end on a bunch of falses for the first bit. Maybe there's some truths. I think what I really need to see happening is for each of these sets of like 9 flip-flops that go into one of the final conjunctions, see how those change over time. Okay, we are drawing. So Rx has going into it MKFPRC, wait, MKFPXT. FP. I should use the same case. I lose my cursor whenever I like zoom. I don't know why I'm not allowed to see my cursor. Okay. Nope. What if I click on the pen? Oh, I guess because it becomes a hand cursor for a bit. Okay, what was it again? MKFP. MKFP. XT. ZC. XT. ZC. Each of those has a single conjunction going into it. LLRCGV. So LLRC. Gross. RC. I think we're gonna draw those as AND gates because that's sort of what they are. Oops. GV and ZC. GV QF actually. UF. And Rx itself is a conjunction, right? Yeah. Um, yeah, I'm gonna draw these like that when they're conjunctions. Maybe I should do it with color. Let's do it with some color. Um, Green for conjunctions because every input has to be gross. Here's a conjunction. It goes there. Conjunction goes there. Conjunction that goes there. Okay, and this is where it starts to get hairier. LL. 9 flip-flops. QD, PD, MR, MX, FH. So we'll do it from here. UD, PD, MR, PD, MR. I should probably do this programmatically, yeah? Um, let's see if we can move these. And how do I grab it? I think I have to use the actual mouse to grab it. One of these days, I'll figure out how to use whiteboards well. Whatever. MXFHCH. MXFHFHZH. VLSQTX. VLSQ. Maybe not there. VLSQ. TX. And we'll just draw like a dotted line. Nothing, I don't expect anything to cross this dotted line. We could use that for determining our arc. Okay, what goes into RC? It's these 9. CG, DH, NZ. G, TH, and Z, and FB. I think I'll just go down one of these branches and forget about the others for now, just until I understand. So NF, FB, LD, DDVJVL, DDVJVL, Should run. Hello, hello. Okay, and these are all flip-flops, which I'm just gonna show with red. Um, fix. And do these have other destinations? So there's certainly these. Yeah, I'm just gonna draw enough of one of these graphs so I can understand it. But I think I understand the general idea of what's gonna happen. Because like at some point all of these need to be ones, right? These have like interactions with each other. I think we need to like count their interactions with each other. There's some like conjunction going on. Um, there's a weird pattern I noticed. Uh, where is it? Oh yeah, each of these. So each of these has like a special flip flop. Inputs are the broadcaster and a conjunction, which has some more of these as inputs. So we'll figure out which one that is and we'll circle them. So for this set, the ones going into RC, it's been a long time in touch Scala. Uh, you mean you haven't programmed in a long time? So into RC, let's look at this. The special one is VJ. Where's VJ? Let's circle that. And what's going into VJ? There's a broadcaster. I don't know, I think I'll put a big B for the broadcaster. Like clear out here. And the broadcaster only goes into these four. So that goes into there. And in the LL map, there's LL, the first one. The broadcaster goes into FH. Circle FH. And, you know, you can get the idea. Like these all point down to that. So I'm just going to like better. What's this one on the right side that we're going to analyze? We're using this main programming language for Spark. Makes sense. Spark was big draw for Scala. Are you still doing data engineering? FH. So going into that is a broadcaster and also LL. Wait, the conjunction named LL. That's this conjunction. And these things feed back into LL. Oh, no, no. This conjunction here? Oh, wait, for LL, yeah. That's all feeds. RC feeds back into this. Okay. So RC feeds back into VJ. I'm gonna draw a bigger line than that. One of these days I'm gonna get a drawing pad that also has a touchpad capability so I can scroll around. Interesting. I mean, this conjunction. So RC has other destinations, I suppose. Let's look at that in here. Hmm. Yeah, it goes to VJ FP, which. Oh, yeah, that's fine. EF, KQ, and VF. Now those appear here. So I'm going to draw them out here. So we'll say VF. Wait, let's make sure it doesn't appear elsewhere. I think I already did that in here, right? VF. I probably drew an FP somewhere. No. DF is one of the other flip-flops. KQ is one of the other flip-flops. VF is one of the. So these three. And then another flip-flop outside this altogether. GF, KQ, and VF. Wait. RC. BJ. Was this FB actually an FP? FB. GF. Wait, GF is not in here. None of these exist here. No. GF is that flip flop. That LD goes into. So LD also goes into that flip flop. And NF also goes into KQ. And CG also goes into VF. And FP is a mystery. We'll draw those three. VF, KQ, VF. Mm. Where's my cursor? Why does it do that to me? And are all of those flip flops? Those are all flip flops. And then there's an unknown FP somewhere. Okay, those are all flip flops that have destinations, but importantly, other flip flops go into them. So what goes into VF? CG. CG goes into VF. And what does VF go into? Wait, VF goes right back into CG. So this is multi-directional. And CG also goes into there. Okay, interesting. Let's look at KQ. KQ goes into NF. KQ is back and forth with NF. Okay. What was I again? KQ back and forth into NF. and then GF. Oh wait, we already hit no, GF is new. Goes back and forth into LD. You know what? I'm gonna choose a new whiteboard app. I don't like this one. GF and LD. Okay, so I'm going to think about the nature of what those things do. And I'll have to look at what FP goes into. These others, I'll go. So these are the three that loop back into themselves. We can see it here. And then these other four, three of them go into RC. FL, DD, NZ, RC. Hi, Nicole. You draw those. Okay. Wait, FB goes into CG. The flip flop, the destinations, FB and RC. Yeah. Okay, let's look at these one by one. DH. I'll just go take that to NZ. Let's draw an NZ close to DH. Where's DH? So we have an NZ. Oh, wait, not NZ. NZ goes into LD. LD goes into NZ and RC. That goes into ND and RZ, which don't appear anywhere else, right? LD goes into NZ. Oh, it goes back into itself. Okay, and then RC, which is another thing. Oh, the conjunction. RC is the conjunction that goes into VJ, the one that the broadcaster goes into. Okay. That's an important conjunction. Draw that one out. RC. So that goes into VJ. We'll draw a big arc around it. And now we've gotten to that because we were looking at LD, which goes back to NZ. This is bidirectional. I'll have to think about what a bidirectional node implies. Then into RC. should actually draw this in terms of circuits. I don't know the symbol for a flip-flop, though. The greens are just AND gates. Okay, so we had LD. Or, whatever DH was doing. Now let's look at whatever NZ is doing. So NZ, wait, NZ goes to LD? Oh, fine, yeah, we handle that. I guess we skipped over DH then. DH is the only input to the conjunction that goes into VJ. Wait, what? Oh, and the conjunction, wait, but I thought LD went into there. Yeah, LD did go into there. Oh, right, wait, we skipped ahead. LD goes into the conjunction, but the conjunction doesn't list LD as an input. That's weird. Okay, well, we'll trust the destinations anyway. LD goes to NZ and RC. NZ goes back and forth with DH. Oh, wait, NZ here. Oh, no. Oh, okay. It goes back and forth with a neighbor. Oh, no. So NZ goes to LD, which goes to NZ, and then goes to RC. Right? NZ goes to LD, which goes back to NZ, and then LD also goes to RC. Is NZ not the name of this flip-flop? N and modules N. Wait, each of these lists the modules that goes into it. Modules that filter destination contain. Yeah, so NZ, this is the list of modules that go into it. Right. So let's just make sure we're doing this again properly. CG, VF goes into it. VF goes into it. Okay. DH, NZ goes into it. NZ goes into it. And NZ itself goes right back into GH. But this is bidirectional. It's seeming like all of these are going to be bidirectional. And then I guess this also goes. We should have like an input side and an output side to each of these gates. But oh well. So this also goes into RC. And I'm going to have to double check main graph for the input, actual input. NZ. So LD goes into it. I'm just surprised that these don't match up flip-flop destinations. Because this is the destinations of NZ. Oh, these are things that go into NZ. Okay, yeah, we don't have the destinations for any of these things, which we should probably just get their destinations. Okay, we can do that separately. What we care about right now is what goes into it. Oh, LD goes into NZ. Yeah, we've done that. NF, that's handled. KQ goes into it, and KQ goes back into NF. Right, there we go. FB. What goes into FB? CG goes into FB. CG goes into FB. Where's CG? Okay. CG itself goes into FB and RC. And it goes like CG goes into FB and RC. And FB, well, yeah, all we have is that CG goes into FB. Oh, I hope I'm not misinterpreting this. Are these not all bidirectional? CG, oh yes, this is not bidirectional. I'd read this as bidirectional, but this is a source for this, not a destination. Hmm. Okay, I might have to redraw that. Okay, those are not all bidirectional then. And we'll have to sort those out. Okay, CG, you know that VF goes into CG. VF goes into CG. I should have drawn VF up there. Well, let's keep drawing this out and at least get an idea, and then we can clean it up later if we need to. LD goes into NZ. LD goes into NZ, sure. Um, NF. We've handled that. CG goes into FB. CG goes into FB. Yeah, we have that going on already. And RC goes into, okay, so RC, DH is the only one that goes into it. I'd misread a bunch of these. RC is actually going into those. Destinations, GFK. RC is a conjunction. Now VJ is a big important one, right? I'm calling it important because that's the only one that RC goes into. 21 Blue 3. Hey there, first time here. I just read your bio and thought maybe you could share some advice on how to become a good dev and front-end or dev student using JavaScript React. Perhaps. I can't say much about front-end. And honestly, right now I don't feel like a good dev. If you have any more specific questions, maybe I can answer those. But to come up with something right now, my mind's kind of taken by this puzzle here. I'll probably call it quits at 4 a.m. Okay, we're gonna try again here. And a little bit more explicit. So we'll take this into LL. We'll print the thing itself, and then the things are going into it. Its name, Its module. Where is that? Down here. So here's the name. um, Modules and the name its module, and then the things that are going into it, and their names and modules. And let's do it like this way. Okay, that should do it. Unable to worksheet. What's wrong? Okay, we can export the worksheet again. Okay, let's look at the LL list up above. We can understand that one, and we're in a good spot. I'm gonna move some of these around. I don't know. I don't know how to move a thing. Nope, nope. I can't grab it. Okay, I'm gonna delete it. I'm gonna delete it and redraw it. So this is MR. Here we go. MR goes up here. Strivewinkle, yes, yes, I did manage to get it done. You remember at the end we were talking about unions, and I justified it. No one really pushed back on it. My justification was bullshit. So all I had to change for that was so in my search I gathered all the unions, right? And then I or not the unions, I gathered all the ranges that hit and accept. And those ranges are each individually correct, right? And what I was doing yesterday was taking them and I was collapsing them all down. So I was like taking unions of those ranges. All I had to change was instead of picking unions of those ranges, I just count how many was at each of those, how many combinations each of those ranges had, and I summed them instead of taking the union. And that was it. That was it. The code? The code is a lot simpler. This is my search code now. That's all I had to do. Right? If it's accept, we count the combinations. If it's a send, we do recursive search on those ranges. Right? I have my incoming ranges and I filter any action ranges I get by that. If it's a reject, I just add 0. Yeah. So between action ranges and search, this is where most of the logic is. And it feels a lot cleaner. There's parts, my model's pretty verbose. There's like too much code here. So I still want to refactor this, but I don't know. I'm happy. Okay. Uh, and now, excuse me. Now for day 20. I don't know if you finished it yet, but I'm still trying to understand enough of the structure that I can come up with an efficient solution. What is this big arrow? That's from the button. Okay. The button goes there. And then there's some conjunction in here somewhere. There's a conjunction named LL. Oh wait, that's this conjunction. This conjunction feeds back Um, Inputs are SQ. Yeah, one of the other flip-flops. Destinations of LL. So we have MK. That's well known. That's one of the final conjunctions. FH, which is the one that's being broadcast to. So I'm gonna like widen this here. And all of these feed into here, right? Those are all sources. Wait, LL conjunction. I thought my conjunctions had their lists of sources. These are all the things that have LL as a destination. I guess this is just wrong here. Except it gives me the correct answer for part one, so it can't be that wrong. We'll see. We'll look into that later. But this conjunction has its destinations MK, FH, VG, VZ. Some of these are here, right? One of them is at FH. So we'll like loop that back. VG, ZB, and DM. And those should all appear here somewhere. So VG. Yeah, it's one of the destinations of VL. It has TX as a destination. Yeah. So we'll put near TX. VG. And these are things that LL goes to. So let's look at ZV. Where else did that appear? It has MX as a destination. So ZV goes up here. ZV. And then L1 DN. That has QD as a destination. DM. D. You haven't done 20 yet. You started December 10th and never caught up. You're still on 12P2. Wondering if there's a trick other than memoizing. Can't remember day 12. Let me look it up real quick. Oh, okay, yeah. I don't think there's any special performance tricks you need. I do use a memo. Okay. There is a special performance trick. I forget what exactly part two does. Okay, so if you're thinking it needs a memo, I use a memo for whatever that's worth. Okay, back to the drawing. So each of these things that we just drew, they are going into the thing that they're next to, but the big conjunction is going into them as well. So let's draw out that line. Actually here, we'll say this here was a flip-flop. These are all flip-flops. Flip-flops, right? And this here goes into that, and into that. And then also into something else called ZV, or no, FH, which we don't see here. Oh, we do see it here. That's not one of the ones that's already drawn, right? I can't scroll. FH. Oh, okay. That is one of those. Oh, yeah. FH is the main one. FH, MK. What's MK? Right. MK shows up nowhere else. Oh, wait, no. MK is here. So the conjunction, the special one, 3, 4, 5, and then 3 on the outside. Okay. Great. Let's look at each of these where they go. VL. Or you know what? Let's look at these that these things had gone into. So QD. I've got a little bug on my microphone. Let me just. I have no clue where they went. Um. My cursor has a tendency to disappear. I don't know why. Okay, we'll look first at QD. QD goes to LL and MR. LL is well established. MR is one of its neighbors. That goes to MR. I wonder if I should draw the line like in the other direction. Hit it from the back. Nope, I don't like that. But that hits MR. MX, what does that hit? MX hits DM. DM. That's a new name. Have you seen that? That's one of the ones that goes into QD. DM goes into QD. Oh, right. Yeah, we have drawn it there before. Okay. My cursor keeps disappearing. I don't know why. Alt W to switch to inking. Okay. So MX goes into DM. And ZV goes into MX. Or rather, so QD. Let's look at QD. QD goes into MR. Oh, right. And DM goes into it. Yeah, that's established. We've been doing this because MX goes into DM. Okay. Just look where each of these goes into LL. Wait, FH goes into LL and VL. So FH goes into VL. I should have like drawn these in their order before like putting them out here. FH goes into VL. Where's VL? Oh yeah, that's one of the neighbors. FH is the one that has a bunch of things going into it. SQ only goes into LL. PD goes into SQ. Mhm. PD. Oh my god. These pens. Oh, wait, what did I do? Oh, it goes into SQ. PD goes into SQ. Oh, the mouse. MR goes into PD. TX goes into ZH. TX goes into CH. I'm gonna have to reorder these. And where they're going, because it seems like these form a loop. And then TX goes into CH, CH goes into CV. CH goes into ZV. Where is ZV? ZV is one of the destinations of MX. Oh. There we go. And which one's that? ZH. How do I draw this? Okay, so these do form a line, right? ZH goes into ZV, into MX, into DM, into QD, into MR, into PD, into SQ. Wait, what does SQ go into? SQ, and SQ only goes into LL. Hmm. Yeah, and then VG here. VG goes into what? Where's VG mentioned? All the things going into TX. Yeah, VG only goes into TX. VL goes into VG. VL goes into VG. I think I'm on the verge of understanding this because I'm seeing the loop now. Yeah, it's a full-on loop. Um, yeah, and SQ only goes into here. If we follow that backwards, VH, TX, VH, VL, FH. Right. So these all form a line. And how many of them are in that line? And then the interesting part here is these conjunctions. Oh, okay, this is binary. This is binary. We just need certain numbers of this. Okay, when you sequence these flip-flops, you give it a low, you give it a low, it turns high. You give it a low, it switches back to low and gives a low. Right? So it passes the thing forward. Yeah, these are binary counters. Okay, I've got it. We just need to count how many each of those. How many are in each of those? Ah, I don't even need to draw it nicely. Um, so how do I discover this programmatically? We look at the button. Button goes to FH. We see how deep it goes. We can do a little simulation. Okay, I might have to think about this while I pee. But basically, on the first button, this lights up. On the second button, well, this lights up and sends a high, right? And then 0, it goes back to 0, and this goes back to 1, right? And the number of button presses we need for this to go white or whatever. And then these conjunctions, we just like multiply them, like the low LCM. So for this one, we need 0, 0, 1, 0, 0, 1, 0, 0, 1. Yeah. Okay, 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 0, 0. Oh wait, the very first one is also connected, so the very first one needs to be a 1. So 0, 0, 1 is actually 1, 1, 0, 1. So 1, 0, 1, 0, 0, 1, 0. So here's the first one, second one, third one, 1, fourth one, and then how many zeros from there? 0, 0, 0, 1. 0, 0, 0, 1. And I could read these off. I could read these all off from my worksheet. So we write the order. Yeah, we write the orders for each of those. 1, 0, 0, 0, 1, 0, 1, 0, 0, 3 zeros, 1, 0, 2, 0, 1, 0. So LL 1, 0, 0, 0, 1. Whoops. 1, 0, 1. What happened here? Okay. 0, 0, 1, 0, 1. Should have expected a counter. Okay. Now the button. So broadcaster, it's a bunch of things. But which one of these is in this list? VJ. So we'll write down the order there. VJ, which goes to FL, which goes to DD, which goes to VF, which goes to CG, which goes to FB, which goes to KQ, which goes to NF, which goes to GF, which goes to LD, which goes to NZ, which goes to DH. This is awfully long. And DH just goes to RC. Oops, I wrote HD. And because that goes to RC, it also needs to be whatever. Okay, and this RC, need to figure out what it goes into. These five. So this is one. Nope, Copilot, you're wrong. You're drunk, go home. So, what would matter here? What is FP? Mention that all. FP does not seem to be mentioned. Are we missing a link? What if it's actually. No, this is printed out. Okay, I'll be right back. Yes, I'm on part 2, and I've figured it out. So I'm just reading out my answer right now. Also, welcome, Alka. Are you still online, or did you end your stream? And did you solve today's? FP is missing from this data. I'm gonna look up here. FP. FP goes to KL. Oh, right. FP is a conjunction. It's this thing here. Wait, that's another conjunction altogether. This conjunction goes into another conjunction? Is it conjunction? That's one of the main conjunctions that goes into L. Oh, right. Yes, yes. Of course, it goes into one of the main conjunctions. Right. We just want what things that go into this. RC. Let's look at RC. Or, oh, hold on. Oh, no, no. That's not what you want. I struggle so much with this whiteboard. It is not the best UI. So here, like there's a thing that goes into R conjunction LL. Something goes into R conjunction RC. Uh, yes, this is VJ goes into R conjunction RC. It also goes into FL. Does this go into a full loop? Okay, looking back at this one here, FH goes into LL. Right, where's FH? You have a conjunction named LL. SQ goes into it. Oh, SQ goes into it. Did I read this off wrong? Where did I get FH? FH. FH is the thing that the conjunction goes into, rather. Oh, yes, right. That's what this green means. It's one of the things that the conjunction goes into. It goes into a bunch of other things too. But it's a thing that the broadcaster also goes into. Okay. Yeah, the thing that the broadcaster goes into. We're gonna traverse the order of this, by the way, is VJ here. VJ. Um, which one of those? VJ, AQGF, what are those? Uh, should I do this programmatically? Give me a vote. You think I should do this programmatically? You're not trying to optimize. Yeah, you don't optimize it. You reverse engineer it. Okay, here's a one. So VF is here. What is KQ? KQ should appear in here somewhere. KQ goes into NF. Row right is right here. And then GF is right there. Okay. So I need to reverse this afterwards. 0, 1, 0, 1, 0, 0, 0. And DH goes into RC. So that's the highest bit. This needs to be a 1 as well. Well, it doesn't need to be. Just everything that's going into RC. Oh wait, RC has destinations. I don't think the destinations are what we want. I think we want the things that go into the RC. Okay. Now let's do this a little bit more programmatic. RC. The things that go into RC are ones. This can be too error prone, so you have to write a program. And you know exactly how to. Into RC. Oh, wait, they all go into RC. We want the ones that RC goes into. So modules, RC. And for each of these, we know the main one that the button hits, right? Oh, um, yeah, the button hits a flip-flop on each of these loops. Modules, broadcaster, destinations. Val, 0 bits. And then 0 bits dot map. And then for each module, we'll call this a name. This is the name of a 0 bit. We are gonna unfold. We're gonna keep recursively taking other flip-flops. So modules and LM. Modules given that name, not as instance of flip-flop. We're being crazy here. Horrible fart. Thank you for the follow. Iterator.unfold. So we start at M, this module. And at each location, I mean, we know it's a flip-flop, right? Option.unfold. That's gonna be something. You look at the destinations. M.destinations dot select first. That is not RC. Case. Well, I can actually map each of these. Map each of these to modules. And case flip flop. Nothing else matters. You're just unfolding each of these bits. And we want to know right, we need the module name so that we could check what goes to it. So we have a dest. And then val 1. And this will be modules dest dot exists. You get people happy. Oh, well, thank you. Thank you. Thank you for the raid, Alka. Party of 20. So I'm working on Avocode Day 20, and I know what it is. So this is spoilers. If you haven't solved it yet. So you push the button, right? Oh, this is a broadcaster. The broadcaster goes to 4 different flip-flops. These flip-flops are each into a chain of flip-flops that goes all the way to some conjunction here, right? And this conjunction, all 4 of these outer conjunctions here need to be green for Rx to be green, right? So we have this big chain, I guess from FH eventually to something. I don't know, something. There's some final element here. We could trace it. Yada, 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 to SQ, right? So SQ is going to be like our big end, our highest bit. And now LL is watching some of those values. And the values that it's watching needs to be 1. So every time this pushes, this turns into this flips flops between 1 and 0 every time you have a button push. And then every time this hits 0, the next one increments, right? So this whole thing is just an adder. This whole thing is just a counter. And these green lines here tell you which one of these need to be on, basically, which translates to binary number. So there you have it. There you have it. And this is one of my numbers. And I need to take the least common multiple of the 4 numbers that we get. I'm just doing it programmatically now because I was doing it. I mean, I was reading off of this, but this is feeling very error prone. Um, so for module, I don't know why it's not happy with that. We start with that module, and we have to determine if it's a 1 or not. Oh, hold on. Just have to determine the next module if there exists one. And then we can separately determine if it's a 1 or not. So module, I guess we look at things like go. See if a conjunction goes to it, right? The only conjunction that should go to it would be like this one here, one of these out of 4. That filter, that destinations, that contains, wait, 0 bits. These are my list of strings. Yeah, these are names. We get the module. I'm gonna call this name. We're gonna unfold from that module. And to determine if it's a 1, modules that exists something that is that is a conjunction. So we have to do a case here. Case junction yada dests if dests dot names name true. Just need a single true to happen. And we'll say this is in fact a 1. Otherwise is false. And 1 is what we're going to be returning here. And then we have to get the next location. So m destinations map. We want to flip flop. So dests, and then we take modules of dest, and there should only be one flip flop. And that will be the new module. Hold on, where's our unfold happening? Yeah, for this module. And do each of these, okay, each of these might have multiple destinations, one of which is an RC, and one of them which, okay. Um, no, and not destinations. Wait, we're gonna map those to modules. These are modules dot collect first case flip flop. This will be next m case flip flop. Whatever, things don't matter here. If something is a flip flop, let me return it. And then next m dot map. One to whatever it is. Let's worry about the final case here. We always have to return. So if there's no next module, we don't end up returning the current thing. Oh, you know what? Let's do it this way. So we're gonna do case flip flop, and it's gonna be a sum. And in case anything else, it's gonna be a none. Wait, if this thing, okay, that's completely wrong. But we're gonna have one to whatever the next module is. I think this should just be a name. So we'll pass a name in here. And we're gonna do modules of that name. Modules of whatever that thing is. And match. If it's a flip-flop, then we return one, we move on to the next, and val next. Not find. We're gonna do the collect first. If modules. This is the dest name, modules dest. Is instance of, we're just gonna do an is instance of check. No, we should map modules, dest map modules, not collect first. Case, ff flip flop, just return that ff. And that get or else. Otherwise, you just get whatever first thing is in there. Dot head. And then one goes on to the next state, one being defined here. Oh, if there's a conjunction, right? Bingo, bingo, bingo. Um, these are the 0 bits. So for each of those, we're gonna do like an iterator.unfold. Um, you know what? That one, we're gonna do bit unfold starting with name, right? That shouldn't be an issue. Uh, okay, I guess we have to write it this way. And val bits. This bit is just gonna be 1 or 0. 1 or 0. The first bit's gonna be the least significant, so we have to reverse them. Bits dot make string dot reverse, and then integer dot parse int for those bits base 2. One is actually the bit. Yeah, that's a char. Oh. Fine. Just do this real quick. Val bit if 1, then 1, else 0. And I guess it's just true and false again. I can clean this up a lot, but right now we're just being hacky. Dest. Right. Map, let's say n to n and modules. And now case, we have a name and an ff. We return that name. Okay, that should be the right type. Next, or module, dest.not. I guess it's just dest.head. Conjunction. This type module is not a subclass of modules. Oh, yes. And does the name of that module matter? It does not matter. Then we take the LCM of those 4. Is 24/7 prime? Wait, is that 1? Seriously? I don't believe that. Let's print line. Print line bits. I guess we should do list this whole thing. Dot do list. Okay, 111. Oh, where are the zeros? Bit 1 and 1 else 0. Why are we not returning those? I don't believe this. Okay. Um, we start at one of these 0 bits, right? These names. I guess these are like the ones bits. Too late. It's the least significant bit. Take the least significant bit, and we get the next bit. Hmm. Let's print n for each of these. GZ, MZ, PS, GV. And it gives up. That's it. That's all it has. Um, Interesting. Let's look at this. I'm gonna pull up the input on the right. Day dash 20, 2023. So these 0 bits. GZ. So let's look at GZ. MZ and GF. MZ and GV. One of these is a conjunction. I think GV is the conjunction. Yeah. So it should go to MZ. I should start by just getting the sequence, right? A sequence of names. Bit module names. So this will be a shortening of a bunch of this code. You can do a lazy list unfold. Or I guess we could do like an iterator.iterate. Yeah, lazy list.iterate, starting with name. We take a name, we get the next name. So to get the next, we do this kind of thing. We keep taking the next. Oh, hold on. At some point, there's not going to be a next. I'm going to unfold. And then modules. There's an N. Modules N. Match some flip-flop. Then return the new name. If it's a flip-flop, if it's a, this doesn't matter, this case doesn't matter. I mean, I guess in any of these, we have destinations. Doesn't matter if it's a flip-flop or not, really, as long as you can get the next, which is here. Tests. Okay. So we get the name of the module. Otherwise, we take just whatever next name. And we're always going to return some, and it's going to be this current name next name is the next state. And then I'm going to take those file bits, those bit module names, and let's do a take while on this. And so modules n match flip flop is true, otherwise false. I'm making this harder than it needs to be. I'm I'm too tired. Okay. So now bits. What's bits gonna be? Yeah, it's still a bunch of names. And then we're gonna map these. So dot map. Still have the name. And I guess modules dot filter. Dot destinations contains n. Okay, dot collect. Yeah. Case. I don't think we care about flip flop. That code's completely wrong. So these are two modules, these are names. Case. Whatever, and conjunction. Yeah, C conjunction. To return that said conjunction. I guess if it exists. So I'll see. We'll just say that. If C is empty, then 0 else 1. Yeah, exactly that, sort of. And now we have bits, just a list of characters. And we can bits characters, yeah. Nice list of characters. Dot make string. Oh, hold on. Bits dot as digit. Yeah, we can turn them into. No, we shouldn't be using chars there. We should straight up use real zeros and ones. So dot make string dot reverse. Integer dot parse int that. I don't think the last one necessarily is a 1. Let me just make sure integer dot parse int with leading zeros. 0, 0, 0, 1, 0. That should be 4. Oh, hold on. That should be base 2. Yes, that should be 2. Base 2. Okay, that's that. Need to get the module. Modules, destinations. Oh, hold on. We have a name of module, right? Modules n. Destinations. No, we want all the modules. We want the modules that go here. So the modules that hit this. Yeah. The destination, so underscore 2 dot destinations. That contains that in. Okay. 11173 2. I don't know why I'm struggling with this. So let's print line bits. To list. We're getting the same thing each time. Oh, okay. Maybe it's faster to draw this. No, it's not faster to draw this. Maybe it's faster to do this thing here. We get the whole sequence. So LL, we figured it out, is whatever that is. Maybe backwards. 1001. What's the first one? FH. FH, that's a 1. 0, 0, 0. Oh, wait, no. This is 1. It goes to here, 0, 1. Yeah, 1, 0, 1. Okay, yeah, it's from right to left. Cool. That's correct. So this is one where integer.parse ints. And let's make sure we have the right idea over here. The button goes into VJ. Okay. And DH. 1, 2. This is going to be, how many ones in here? 1, 2, 3, 4, 5. And FP, wherever that shows up. I don't know where FP goes. Wait, FP? FP is here. Yeah, so that we can delete. There's too many arrows. Okay, 1, 2, 3, 4. This is a 4-bit thing. 1, 2, 3, 4. Misleading DH then is a 0. DH is the one that points into RC, right? Or that points only to RC. Yeah. And nothing points into it except NZ, so it can be 0. Cool. So this is 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 1. Okay, you got a second number. I can't code. I can do this. So the broadcaster goes into GZ. So GZ. And what is, so GV is our thing. So GZ goes into MZ. MZ goes into PS. PS goes into KX. KX seems to be missing here. KX. It's one of the things the conjunction goes into. Okay, KX is missing here. Let's just look at the thing. KX goes into SS. SS goes into LQ. Okay, LQ goes into TZ. LQ goes into TZ. TZ goes into QH. H goes to VK. VK goes into GK. VK goes into LB. LB goes into GX. And GX finally goes into GV. SGV. Okay, and we need to know what the conjunction goes into these. We can remove GV. Wait, what? Yeah, GV is the main conjunction. Oh yeah, GV is the name of the conjunction. It also goes into XF, which can be XT, which can be removed from here. Okay, easy, so there's one there. TZSS and KX. Okay, so this one's pretty low. So this is 0, 0, 0. 0, 0, 1, 0, 1, 1, 0, 0, 1. Okay, that's that. That's our third number. And our fourth and final number. Okay, which one does the broadcaster go into? JT. JT. JT goes into XR. JT goes into XR. XR goes into JZ. JZ goes into, we don't know what JZ goes into. JZ goes into LF. LF. LF goes into MG. MG goes into MN. N goes into RD. RD goes into PJ. PJ goes into CL. And CL goes into TC. TC goes into TS. TS goes into SG. SG goes into QF. And that's it. Let's look at what QF goes into. So these QF also goes into ZC. So ZC we can ignore here. And the rest of these are our ones. So PJ, JT, JZ, LF, MN. Okay. This is 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1. Make sure it's the same length as the others. Okay, I'll just take those into the worksheet. Uncomment those. And we're going to do integer.parseInt, whatever that is, in base 2. And I guess we're going to put these into list. Oh, not right now. These need to be a string. And then we get the LCM of all of those. And those all look like prime numbers. So I'm just gonna get the product of all of those. So list, and those all with a comma. There we go. Dot product. Val adds 2 equals that. Oh wait, those all need to be long. We're gonna do long that parse int. Or big decimal. Is there a long that parse int? Long that parse. No. I mean, I think those are all integers. Yeah, those are all less than 32 bits. So we just integer that parse int. And then not too long before we take the product. Okay. We finally got it. Batch 2. Val ends 2. Which was this thing? And here we go, here we go. Answer's too low. No, hold on. So what this is saying, every 2,000 cycles, these line up. All of these are lined up. Okay, it's not quite just a product. I think we had the right numbers. Do we Chinese remainder theorem this? So 2213. How often do these same 5 light up again? Let's look at something like so 2213, not 2 binary string. And let's do like times 2. Yeah, times 2 is just going to shift it. So 2213 until the first time. That happens. But we need all of those. Oh, wait. Yeah, so what we do is we zip those together. We need to zip those together. So yeah, this thing, that's not quite right. And I'm not going to parse int. We're just going to zip all of those together. Oh no, we're going to take the, what do you call it? The hat of these things. We're going to XOR them together. Or no, we're going to OR them together. Bitwise OR. You don't need it too long. So let's take that. Reduce. That number seems too small. Let's look at that as 2.2 binary string. It is 1 in all those right places. 2557. Wait a second. That's too low though. Wasn't like 100,000 too low? Was a fewest number of buttons pressed is required to deliver a single low pulse? 2557. If this answer was too low, because these all increment at the same time, right? These are all 12-bit binary numbers. Um, I'm pretty sure I have the numbers. I mean, there might be mistakes there. I did it by hand. Hmm. Someone came in here and said that they ended up with like a huge number, like a 15-digit decimal number. So what am I missing? Let's look back at the graph here. And now every time this is pushed, this increments, right? And this first number is 2213. So after 2000 times, this thing is happy. But we need to have all four of them be happy. Wait, all these other things are also sending signals to this. Wait, all of its inputs, all of them are sending signals to L. All of its inputs need to be green. Oh, wait, and this is feeding back into those. This is feeding back into those, which means this thing keeps sending low bits, right? It only sends a high bit when everything is high. On every iteration, we send this to there. Everything is low, so it's not sending anything out. When do those send out? You're reminded of the Charlie whiteboard scene from Always Sunny. Um, yeah, I don't know how closely you've been following along, Betsim, but I know that these are binary counters, sort of, and then I've extracted the numbers themselves, and I'm realizing it wasn't my first ideas, which is like the product, which I didn't even think about this one. I thought, okay, these are all counters. I need those to be ones. Then we just XOR them, and then I realized, okay, I'm misreading this graph a little bit. And these are indeed counters, but these are all sending signals, so these all need to be sending green signals, not just these. So I misread the direction of these green arrows. These green arrows on everything are sending lows to the, on every tick they're sending lows to all of those flip-flops. And what happens with flip-flops? Flip-flop, they are all off. If it receives a high pulse, it is ignored and nothing happens. Oh, they're never going to receive a high pulse. Right? This is pointing at those five. They're never going to receive a high pulse. I mean, they are going to receive a high pulse. Like, eventually, that's going to hit 11111. And when that does happen, oh, hold up. So this increments. Eventually, we reach whatever this is. We should do 12 ones. 111, 111, 111, 111. Let's make sure it's the same length as one of these. Yeah. So after that many things, I'm so close I can taste it. So after 495, then that thing sends out ones to all of these. So the next state is going to be it sends a high pulses to all of those. Um, Wait, they swap on a low pulse though. Do they swap on a? Okay. If it receives a low pulse, it flips between on and off. Oh, okay, never mind. If it was off, it turns on and sends a high pulse. Yeah, I misread that. That's still cool to know that number, I guess. Um, Means those are on like double duty. So on every tick, and one exactly. Oh, it receives like that many actions. It's gonna receive 12 actions. So first a button comes in. This sends an action to that. It sends things to everything that's list. Does the order matter? So day 20 input. Um, Look at let's look at LL, or let's look at FH. FH goes to LL and VL. So first it sends a tick to LL, which increments everything. So the very first state go through these. You have a bunch of zeros. And then we go to the one. The one sends a tick to LL and VL. So it sends LL gets its tick, VL gets its tick. And then LL sends out all of its ticks. So VL gets its tick. It's going to be a high. Nothing happens quite yet. And then that sends all of its low bits. And the next step, this becomes, oh, hold on. Let me pull this up so I can have it for reference. This gets flipped here. This gets flipped here. This gets flipped here. This gets flipped here. And that gets flipped here. Okay. Those ticks go out. That happens. Low tick was sent to whatever. Um, yeah. So it gets XORed against that number on every tick. Now this goes up to, hold on. That happens because this turned into 0. It sends out a pulse, the one next to it. This becomes a 1. Right, and this is all still after the first button. First button flips that. Causes a flip to that, to the big one, which sends ticks to everything. It also sent a high tick here, which does nothing. This sends a high tick there. All of these Newly formed ones send high ticks that mean nothing. Okay, so this will be like the end state, right? And then at the start of the next one, we again do a 1 here, and it goes high. Nothing happens. We XOR it with this. Um, right? So there's a 1. This sends out a high to all of those, 0. Um, yeah, the 1 and 1. So that becomes a 1 there. I guess you add it by itself. Are we like multiplying? That goes to you take that number, add 1. You multiply it by 2. Um, this becomes 1, and this becomes 0, but it overflows. Are we just shifting it then? We keep shifting to the left. Okay, you XOR against that number. Add 1. XOR against that number. You add 1. I guess it's not quite XOR against it. You just add that number. That function is adding when you throw a bunch of 1s into there, because if they are 1s, then they will cascade over. Yeah. Okay, so you add it, add 1, add it, add 1. And I guess it's saying at what point do all of these become 1s? Um, I guess this was a special case because this thing has a 1. Made the first. Oh, they all have a 1 bit here. Yeah, the 1 bit of all of them is set. So every button, you add 1, and then add that. Add that number. If you keep adding 1 and adding that number, when will it be all 1s? Uh, okay. So 2213. So we start with 0. Then we add 1. 0 plus 1. 1 plus 2213. Um, 2214 plus 1. And 2213 plus, I guess, 14 plus 2213. Let's take that to binary string. Oh, if you're essentially adding 2214 every time, which multiple of 2214? Has just all ones on the right hand side. So let's do 2014. We'll iterate. Iterator dot iterate, starting with 2214. Plus 2214. And then we're gonna map to binary string. And then let's take like 100 for each print line. Doesn't look like that's turning into ones. Okay, I'm misunderstanding something big here. Right, a button comes in. Without this thing. Oh, wait. Depending on the number of ones, this L will be triggered multiple times, right? If it gets any single low tick, it will respond with a low tick. And anytime a digit changes, well, that's going to be some low tick or high tick. But it will send out a low tick. So anytime a digit changes, it sends out a low tick. So the first time through, you know what? I don't need to do it this way. I can actually do this in code. Okay, so somewhere in here we're looking at states. What we do want to know though, we want one of these things a button looks at. Let's look at, I guess, all of these, which is in my scratch somewhere. No, hold on. Scratch. Zero, zero. Okay, here we go. Let's look at RC. These are in reverse order. No, let's not look at that. It's one of these latter ones. Into QF. Let's look at QF. That's gonna be in order from, I'll just bit the smallest bit. Val QF bits equals that split at the space. And we'll list that. And we need to be able to take a state. So let's say presses 0 or qf bits dot map. So we have a bit and presses 0 dot underscore 3 is our map bit match on. It's going to be a flip-flop. And we'll say if on, then 1 else 0. Right? And then we can do this. So presses dot take 10 dot map. We'll call it p's p's. And then here's the val bits equals that. Bits dot make string. And for each of those, we can print line val qf binary numbers. qf bins for print line. Okay, how does it progress? Oh wait, it does progress like a counter. Okay, if it does progress like a counter, I want to look at FH specifically. Well, hold on. You have QF in here somewhere. QF is the fourth one. And QF, it's this number, right? Okay, we still want everything to be ones. I mean, if they're all binary counters, why don't we just do it? What was that 1111? Where is that? Why wouldn't it just be this? Integer precedent of that. $4095. Right, if they're all being counters, why wouldn't it just go to 4095? Because when it hits that, when it hits this number, no, every time it hits 4095, those change. Okay, so you hit 4095, and then this number here, this other thing, gets applied to that, and I guess this bit shifts. We hit that, it throws out a green. Wait, do conjunctions just not return anything? Maybe I misunderstood conjunctions. If I remember, as high pulses for all impulse. Oh, wait. Yes, so they ignore high pulses. We'll send a low pulse. when it has only high inputs. Every time it hits 495, it sends out low pulse, which causes these to increment. Um, so if you send a low pulse to that, right, then that one becomes a 0, and well, I guess you add 1. Oh yeah, you just add these two. So every time you have 4095, okay, if it has high in it sends a low pulse, otherwise it sends a high pulse. So it keeps sending high pulses, so that's why there's a double, right? It keeps sending high pulses to this. And once it sends a low pulse, so at 4095, all of these send low pulses. Wait, at 4095, they all send low pulses? If that's the case, it's a low pulse. All the inputs for this are low pulse. And this last one's a conjunction too. Okay, so Rx, for Rx to be green, all of these need to be low. For each of these to be low, um, so for Rx to be green, we need all of its inputs to be low. I was looking for one where Rx pulses once and exactly once. I mean, Rx will pulse multiple times, but we need to be exactly once. Let's write this down. All right, I guess Rx needs exactly one pulse after all of these have last pulse high. So machine turns on when a single low pulse is sent to Rx. Oh, so I mean any of these can send one, but only one of these must send one. Okay. Makes sense exactly. So Rx must remember all high pulses. Action. Yeah. Rx remembers um, only high pulses. And it first updates, I guess, wait, they first updates its memory. It must only be updated once. It receives a single low pulse. So from the fourth, I guess these each only pulse low very occasionally, right? So Rx has 3 high, fourth high, it's no low hits. I should be writing that in the text editor, not drawing on screen. Um, so those all need to be high, and for those to be high, all the inputs. Wait, no, 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 no. High for all input. That's into low. Right, so each of these needs to send a high. The default state here, most of the time, these are sending low pulses, right? So these are sending low, low, low. And sometimes I guess it's sending multiple. Yeah, so most of the time it's sending low pulse. No, 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 no. Most of the time it's sending high pulses. Its default is high. Sends a low. This is a NAND gate, not an AND gate. I can't keep track of this. Okay. If all high, then low. Otherwise we send a high pulse. So most of these are constantly sending high, 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 right? And then every 2045, they all will send a low. But the thing is, we'll send a low, or every 4095, they'll all send a low. That will send a low, that will send a low, that sends a low, that sends a low. And get 4 lows sent here, which means this sends um oh, let's take a look again at all of these states. Presses. What are we doing about suppresses? Okay, these are a bunch of actions. We want actions that touch Rx. So for each of these list of actions, dot filter dot dest equals Rx. Okay, so the first time it gets a bunch of highs. It gets a lot of highs. And the group map reducing those. Dot group map reduce. So we group them by the sender. We map just a second bit. I guess just group map is enough. I guess we want the counts. Just group map it for now. And we'll do a for each line. Okay, after the first press, KL. Oh, KL is the only thing that goes to RX. Oh, hold on. Yeah, these are always KL, aren't they? I forgot about that. Those don't go directly to RX. Okay, so KL is then the input. Uh, this is RX. Okay, then let's look at what happens to KL in each of those. Okay, so that's our first one. I guess let's get a bunch of lows. The first time there's nothing, right? No action set KL. The second time we get a bunch of lows. We get 4 lows. And we get 2 lows from each of those 4 single low. And interestingly, some of them went to 3. 1, 3, 1, 2, 1. Hmm. Hmm. They ever get highs? Did KL ever receive highs? This sends a high. Whenever it receives a high, I suppose. Yeah, whenever it receives a high, it'll send a high. It's not the 4095, or maybe other things too. That sends a high. Oh. What are people doing on this one? Um, a few people have finished. The 20. Wow, a bunch of them finished in the last hour or so. Mm. Mhm. I guess I could still gain points. No, no, not quite yet. I'm retrying to understand this. Seems like this operates like a counter. I want to see when it departs from being a counter. So where did they have that? I guess QF, QF, QF bits. Take 10. Let's take 100. Well, how am I going to see if there's discrepancy? Hmm. I'm going to put a take 10 here. And now I'm going to do is uf bins.map integer.parse int dot zip with index dot find case bin I. No, no, that's not what we want. We want um, bin is not equal. We'll do collect first. Collect first. Okay, so where bin is not equal to I plus 1. Let's see if that runs. It could be well over 1,000. Wait. How would that be a true option of Boolean? Let's just do this part here. Oh, hold on, hold on. Collect first case. Let's just make that find. 0, 0. Oh, I guess it does start at 0, 0. So bin is not equal to I. 10 and 2. Okay. Oh, integer.parse int. I need to do it base 2. There we go. Oh, this will take a lot longer on 3923. Ah, and it resets back to 0? Interesting. After 3923. Hmm. Let's look at QF bins. Drop 3920. Take 10. That map and then um, so we take the bind string, and we're just gonna take that and integer sparse int bin 2. And we'll do that dot for each print line. Where that discrepancy is. Huh. I recognize that number. 3922. It resets back to 0 after 3922. My QF is this number. Let's do integer.parse int 173. What does that have anything to do with 3920? So it operates as a counter. It's 3920, and then it starts counting again. Yeah, 7 hours. Oh my God. Well, the stream's been 7 hours. I've been working this problem for nearly 6 hours. Ah, I can't believe it. Um, okay, we're gonna drop 3920 times 2, and then we'll take 10. And let's see if this happens again at some point. Okay, this time it goes, but yeah, again it goes until 3922. So this resets to 0 every 3922. Gee, I really do hope I have those right. UF bits. Yeah, let's just make sure. Map. Um, modules. Uh, filter. Um, destinations contains bit. Okay, modules, map filter. Bits. Yeah. Destinations contains B. Do we want the keys? Um, these are all the modules that hit. I don't which them. Oh yeah, these are all the modules that hit. And some of these are hit by QF. Some of them are hit by the broadcaster. In the right order. I hope I got them in the right order. JT being the least common bit. Okay, let's see where the broadcaster goes. What is it? Modules, broadcaster, dot destinations. And these are the lowest bits. DJ, JZ, FH, JT. Okay. Let's extract these from my scratch file. Here's 0. There we go. Into LL. Oh, okay, here we have them actually written down. One of these is QF. This one here on the far left. QF goes to ZC. Let's make a note of that. QF to ZC. And GC is a little bit too. So these here are in the right order. Let me copy those. Val, GV bits. I should know how to auto-complete this. There we go. Let me do a similar analysis for each of these. And this tells me it's 1, oh. These all, oh, wait, GV bits. GV bits. And I'm just checking, I'm just using this to check my binary numbers for each of these. So this is 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1. Okay. That is indeed 173. I need to figure out its relationship to 3022. Yeah, I don't care about that. 0, 0, 0, 0, 0, 5. Oh, you know what? I could have determined whether the ones are 0 by counting how many there are. So 5 zeros, 1, 0, 1, 1, 0, 0, 1. 1, 0, 1, 1, 0, 0, 1. And is that what I had over here? Let's scratch. 1, 0, 1, 1, 0, 0, 1. Yep. So this is GV. F is 1, 0, 1, 0, 1, 1. LL, I'm really confident about. And then RC. I think this is in the opposite order. VJ is the least significant bit. So RC bits. That's split. With a comma. Comma dot first dot to list. And then we can do the same thing here. RC bits. And we'll check that the number matches. 1, 0, 1, 0, 0, 1, 0, 0, 1. 0, 0, 1, done, 0, 0, 1. Yep, RC. And I want to get the order for LL as well so I could see things like this. But honestly, for now, I can turn this into a function. So bins, def bins, given what? Given bits, which are actually like the bit names. List a string. Okay. And the for each we're doing. Like 4,000 lines. No, we're gonna do a find of each of these. Okay. We don't need this line anymore. Means QF bits. Let's do that for each of these. I guess we don't. We have RC bits and we have GV bits. We don't have LL bits yet. Yeah, so we find each of these, the indices at which they, I guess it's bit names now. Okay, this all happened before 4095. I think I can do something with those numbers. I think those are numbers I multiply. Okay, LL bits. And yes, that's FH, VL, VG, FH, VL, VG, EX, ZH, CV, EX, ZH, CV, MX, MY, QD, MX, MY, QD, MR, PD, SQ, MR, PD, XQ. Okay, that's split. List. And I suppose we could do this thing again to check, but I'm pretty confident about that. Let's do it again. These are all relying on presses, right? So it's memoized. Oh, wait, L bits is backwards. Okay, so we should reverse that. Yeah, I'm glad I checked. This broadcaster should be on the bottom. Wait, FH should be last. Yeah. Two list up reverse. And then we do this. Let me make sure it's actually recomputing. Why is LL still showing up first? Reverse up to list. Did I accidentally have reverse first? I just need dot to list. Well, wait, FH is the least significant bit. I should be reversing them. I just reversing it, not change the output. Oh, you know what it is? This is a bug in the worksheets. You can see because 2 plus 2 is not being calculated. That's not updating the worksheet. Add Java heap space. Oh, whatever, screw you. Okay. We're restarting. And we have those 4 numbers in like the 3000 range. And I can't explain how it gets to those numbers, but those numbers seem significant because that's when the counter resets. And I think I just multiply those, and that's my answer. We should also do this for LL bits. Making sure LL bits is in the right order. LL bits. These are zeros. Weird. Hmm. Some of these have nothing going into them. I think my LL might be sort of wrong then. Or did I just miscopy these? Was the first one actually an F? Uh, was that an FH? Okay, let's look at Scratch. 1001, whatever. Here we are. LL. Okay, the one that the broadcaster goes into, FH, that's the least common. The least significant bit. H goes into VL, right? VL goes into VG. FH, VL, VG. Um, this looks funky. I don't believe there's nothing that goes into FH. Right, if you look at our input, 20, 20.text 2023 FH. What goes into FH? Like, at least broadcaster should go into FH. And that's not being shown here. Oh no, that's the last one. Yeah. XQ. Let's go. What goes into XQ? XQ does not exist. Okay. It must not be an XQ then. Ah, that's my handwriting. TX, I guess, is the last one. How did I read XQ? That's a TX. XQ here. Yeah, this is completely wrong. Let's start. Okay, FHVLVG. FHVLVG. EX DHZV. EX DHZV. TX DHZV. MX DMMR. MX DMMR. MX DM. Wait, that's not MR. MX DMQD. MX DMQD. MX DMQD. MRPDSQ. MRPDSQ. Okay, and then we reverse this. And each of these, that looks better. 101000101. Okay, patch again. 100, whatever. 10100. This is a 0 up here. So I had read that wrong. 101000101. I'm glad I checked. 101000101. So this isn't that big number. It is actually a smaller one. Well, anyway, now that that's correct, I can also have LL bins. QF bins. Did this not save? GV bits. Oh, wait, we need to do this on LL bits. LL bits. or 3923 3767 4007 and 3931. So that's the index where each of those goes back to 0. And when they go back to 0, um, that means that they were all at something before that. Yeah, how's it go from that? Oh, I think we XOR against, I think 1010110. Nope. I don't know what relationship that has to the QF binary. Well, the binary is on the right side. 001. All right, the QF binary 1010101. Oh, okay. It's that number right before 1010101. Okay. So basically, when you the number at which when you like XOR, it causes that to reset faster. So it's like subtracting these numbers. Let's do an integer parse int on each of these. Let's just name it val integer dot parse int whatever string base 2 and take a closer look at this relationship between those numbers. $89, so adding each of those, like 165 plus 3923 is 4088. Are these even in the right order? Oh, LLRCGVQF. So that should go up here. This one was LL. This should be 3931. And just to check, it's like 1329 plus 3923. Right? Those should add to 495, I think. No. Well, whatever. I'm gonna multiply them. So list dot map dot too long dot product. I'm gonna submit this as my answer. Let's see if it's too high or too low. You know what? Here, paste. Ah, okay. I still don't understand how this machine works, but I got the star. I got the star. Ah, thank you, thank you. Jesus, what a problem. Oh my god, this is a fun one. How did we do for totals today? Oh, it doesn't rank you by totals. Oh. Okay, I did fourth total points. Um, 4 points ahead of Jan, which gets me closer to overtaking him. The thing about this leaderboard, there are a lot of fast people that started late. So if I happen to beat some of them and beat Jan, then I can get, and then like they beat Jan, then I can get a big gap on him. 6 points behind. I think I can make that up, right? I mean, if I only beat Jan on the next 3 days, then I have it. But if I also happen to beat someone else, but these people are too fast. This is more competitive than it was last year. And I'm slower. Yay. 6 hours. Not to do anymore. Okay. I'm going to commit this after I close the stream. I'm gonna find someone to raid. Is anyone still working on this? And if doubt it, I feel like people would have gone to bed and given up by now. Coder 2K is working on it. Ooh. Day 20? Let's do that. Good night, Alka. Thank you for sticking around. Oh, right. Coder 2K is, they speak like German. Okay. Maybe let's check if anyone is doing that. Okay, we have a French developer. Day 20. Vaccine allowed. X tree. Here's English. Um, they're still working on part 1. Okay, they're in early stages. They're here before you realize you have to reverse engineer some circuits. So we'll raid them, see how they do. All right, everyone. Have a good night. I'll see you around the rest of the month. Yeah, I do wonder how the fastest people did it. They had to have realized right away like what the machine was doing and then figured out how to extract those numbers. I can't believe I made it through. As a very roundabout. It reminds me of day 24 of 2021, which was reverse engineering a machine. Okay. Well, that's enough for tonight.